Samasdar, our distinguished speakers, Professor Molay Banerjee from IIT Kanpur, Professor Sitabro Sinha from Institute of Mathematical Sciences, Chennai, Dr. Taposh Ghosh and Dr. Orijit Bag from our Department of Applied Science, and I'm Dr. Atrey Biswas, today's coordinator. We are all going through a very challenging time of COVID-19, and a lot of things are being discussed about this pandemic situation. So we thought to throw some light about the mathematical aspect of it, a very popular topic indeed. I like to thank you all of the participants for being part of this webinar, and I believe that all of you will enjoy today's session and will go back with some stimulating thoughts with which you can further work on. Now I shall request our Honorable Vice Chancellor Sir, Professor Shoykot Maitro, kindly to inaugurate today's session and share his valuable thoughts about this webinar. Sir, please.
Okay, thank you. This topic today is a little bit, this unusual and academic, mathematics for epidemiology. They're very nice that our natural science group under the able leadership of Professor Sukhendu Samasdar are organizing webinar on very varied and interesting topics. Computational aspects of applied science, then mathematical aspects of epidemiology. These are excellent things to see. Particularly, this is very useful for our students in this sense that mathematics is going to be one of the prominent and important career prospect for the applied science also. Because in near future, it is being predicted and it is being observed that certain types of jobs that will have lots of opportunities, and amongst these jobs, one of these important area is data science, and there this understanding this mathematics properly, and it is a significant component of this data science, data analytics, then of course machine learning and all these things, mathematical understanding of it. So there has been a renewed this interest and importance of mathematics in applied science as far as the career is concerned. Earlier, these in many subjects, professional areas, whatever we have seen that maybe optimum knowledge of mathematics was sufficient enough to pursue that academic programs. But right now, if we embrace mathematics significantly in modeling many things, in understanding many aspects, that will be giving a real dividend in pursuing exciting career in data science, data analytics, big data, and in analogous areas, machine learning and all these things. Machine learning will be requiring maximum number of these professionals in near future, followed by data science and business analytics, data analytics. So this understanding the mathematics of all these things, all these natural phenomena, all these abnormal phenomena, all these disastrous phenomena, understanding the mathematics will give rise to basically give rise to ignition of our creative minds, of our analytic mind and logical mind to see everything from our analytic aspect. And that's why this is important thing to understand what are the different, because we are also trying to give more and more emphasis on mathematics, and in near future maybe we will have many these different formal and structural programs in mathematics through this basic science and the School of Natural Science groups. And this is just this initiation or curtain raiser initiatives for all these programs, and I believe that very soon we will have different formal programs in mathematics, statistics, and allied areas, so that the students they can get enough opportunity to understand the beauty of mathematics. Mathematics itself is a fascinating subject. If we understand this inner beauty of it, then definitely that will not be confined in academic interest or for doing some abstract things, but it has real life applications in pursuing career in in professional areas, as I mentioned earlier, in data science and all these things. So therefore, this is a nice initiative, interesting initiatives, and I believe that this will be of immense help to our participants and resource persons who have been agreed upon to be present over here. They are well known and renowned in their fields, but Professor Malay Banerjee, Professor Sitabru Sinha, all are well known figures. So they will be describing the mathematical beauty and mathematical these aspects of this epidemiology and all these things, and that will be helpful for our students, our learning community in pursuing professional programs as well as in pursuing research areas in different these aspects, which will be of significant importance for our community, for our country. So with this, I would like to express my sincere thanks to our School of Natural Science, Professor Somajdar, Dr. Taposh Ghosh, Dr. Bag, Dr. Atrey Bishwas, who have taken these initiatives, these good initiatives, and of course, sincere thanks to Professor Sitabru Sinha, Professor Malay Banerjee for giving their kind consent to share their views, their ideas, their knowledge and opinions, particularly in this interesting area. And I believe that all our learning community, all the participants present over here, they will be immensely benefited. And my appeal to all of you is, particularly the participants, take serious interest in these subjects, take proper notes, and afterwards try to make this knowledge a sustainable one by joining this discussion forum and discussion prompt, which have been created as a part of this webinar program. And there we will have ample opportunity to interact with these experts in their doyens in their fields. And definitely by this exercise, what is our expectation? Emergence of a learning community, a knowledge community, that will happen. So thank you very much. I have some other programs, so maybe after some point of time, I have to leave to join another meeting, but I wish grand success for this program.
Thank you very much, sir, for your thought-provoking address and your inspiring words. It sets a perfect platform for our speakers to deliver their presentation in the area of mathematical aspects of epidemiology. You nicely described the increasing role of mathematics in today's life in various structured and unstructured areas of our real life. And thank you, sir, for sharing your thoughts. Now I shall request Professor Sukhendu Samajdar, Director of School of Natural and Applied Science, to give a brief overview about the webinar. Sir, please.
Namaskar, Namaste, Honorable Vice Chancellor, distinguished guest speakers, respected colleagues, participants, and members of the borderless knowledge community. It was the summer of 1988, and I was in New Delhi inside Teen Murti Bhavan, interviewing for Nehru Cambridge Scholarship. The panel was chaired by Sri M.G.K. Menon, the then scientific advisor to the Prime Minister. After the exchange of pleasantries, Sri Menon pointed out to a large poster of a skydiver and asked the first and the last question of the interview. Can you model the fall of the skydiver through this air? I was floored, shaken, and stirred, fumbled. Well, so many variables: gravity, wind speed, shape, viscosity, and there was a smiling, nodding presence on the other side of the table. Pointed out, well, what is the most important one? I again fumbled gravity, and the elderly person suggested, let us start with gravity then. And eventually, through the course of the interview, I was guided to arrive at a formulation that was not too far from the right one. However, I got out of the interview room, rather distraught, heavy-hearted, thought I did not do well at all. And instead of returning back to IISc Bangalore, where I was finishing my master's, I headed towards Haridwar for mourning. Anyway, when I went back eventually to IISc Bangalore, there was a telegram with acceptance awaiting me on the desk of my lab. So this was a lesson in simplicity, in making simplifying assumption without compromising the core of the problem. And today, I would take this opportunity to introduce the theme of the webinar, Mathematics of Epidemics, in that spirit of simplifying and getting to the crux of the matter without compromising the core of the issue. I have just prepared a very brief presentation for people like me. I'm sure there are some in the audience who would like to use mathematics for understanding reality, not just mathematics for the sake of mathematics. So basically, we do a lot of mathematics. We learn, however, it is confined mostly to in the field of mathematics itself and exams and the like. We really do not apply much, or we do not really invoke mathematics, at least in a manageable fashion, to understand what is going on. Now, this pandemic has, to some extent, forced us, because all of us are seeing curves. And I would like to very briefly explain where those curves are coming from. The SIR model of epidemic transmission. R is kind of faded because I'm not going to consider, I'm assuming it away. This is not, it is important, but we are making simplifying assumptions here. Let us say there is a population, the word dean, that is, and some of them are infected and some are susceptible. Now the infected ones, they transmit their infection to their nearest neighbors. The idea is to find out, in this case, for example, the red squares are infected, how the red squares are going to change with time, expressing infected population as a function of time. Now that's a little bit of a complex thing, but at least if we give a bit of a thought, we realize that the rate of spread of infection is actually proportional to the fraction of infected individuals in the population, and that's the important thing, the fraction of susceptible individuals in the population as well. Because in the case, if everybody is infected, there is no more to pass the infection on. And if there is nobody infected, we cannot get the infection from anybody. So it is a product of the two. So let the fraction of the infected, if we designate that as F, in this case, there are 6 which are infected out of 36. The fraction is 1/6. And the fraction who are susceptible, there are 30 out of 36, that is 5/6. So the time rate of, so that is the rate of spread of infection is proportional to both. That is, it is the product of F and 1 minus F. And we can express it as dF dt is B times F times 1 minus F, where B is the proportionality constant. What we have here, if we look, that if F is 0, the rate is 0, trivial situation. If F is 1, rate is 0, trivial situation. However, if F is 0.1, that is fraction 0.9, the rate of 0.09. 0.2, 0.8, rate is 0.16. This way the rate is increasing. The rate of transmission is increasing, and it is maximizing when half and half situation arrives. Approximately half are infected and half are there available for infection. The solution of this differential equation comes to be this, where B is a positive constant, and it actually, B indicates the rate of transmission, the intensity of transmission. That is, if we have higher B, that means it has one person is going to transmit to many. So that is an epidemic situation. If we have lower B, maybe one or less than one, it is an endemic situation where one person doesn't transmit to many. And A represents the initial condition. That is, at t equals 0, when we kind of first get an inkling that there is an epidemic at work, so what is the fraction already infected there? However, this is an algebraic expression, and it is difficult other than for specialists in the field to visualize what this means. So in order to visualize that, before that, I just want to show that there are derivations. The derivations are not that difficult, straightforward. After this, I would like to just show how we visualize it. Just a second. So this is an environment, this is DISMOS. So this is a basically computer-aided environment where we can plot the graphs. And it is, here the graphs are not just static, I will just show in a second. Here, these are not static information to consume. This can be in a dynamic environment where one can think, they explore the graphs and learn in an autonomous, active, and dialectic fashion. So this is the shape of the graphs. So these are, for example, this is for initial condition 0.005 at t equals 0. This is the initial condition 0.005, and this is some sort of a condition where 0.5, that is at t equals 0, half of them are already infected. The beauty is I can play this graph, I can change the B, and the graph shape changes. So if B is getting higher, higher and higher, the rate of transmission is changing. And it is rather visible. It could be done this way as well. And we can get the rates also. So the rate increases and eventually peaks, and that is the word that we hear, that, oh, well, when it is going to peak, and then it gradually comes down. So this is a rather simple explanation. However, for many of us who are not specialists, this is an explanation which is rooted in science, which is rooted in mathematics, and which is rigorous with certain simplifying assumptions, of course, but this is not just conjecture or hand waving. Now, once we know, this is the concluding slide, here we have two things. One is, this is a typical 2x2 matrix of the probability of the event and the impact of the event. In this case, the impact of the event is basically mortality, if I may replace that, the high rate of mortality or low rate of mortality. And the high rate of transmission, that is the probability of someone getting transmitted is high. In this case, it is low. Here, high means basically the B is high. Here, low, the B, that is the rate, the intensity is higher. So we have 4 quadrants where low, basically low rate of transmission and low rate of mortality. There is not much in terms of strategic response. So maybe we could ignore that. Comes a situation where the rate of transmission is low, however, the mortality is high. In that case, one approach could be containment. Now, here again, let me categorically say that I am not an expert, neither am I a policymaker nor an epidemiologist. So these are not prescriptions to be followed, but these are certain ways of looking at it so that we can make sense of what is going on right now in a logical fashion. The third quadrant is actually very intense, where the high rate of transmission and the mortality is high. Now here, this is a little bit of an interesting thing happens, that if the mortality is high, the people who are getting sick, they really do not get much of a chance in terms of however long they're living and all that to transmit it. So usually this really kind of dies out often, this kind of epidemics. But however, one approach could be to treat and prevent. Again, the one where the rate of transmission is high and the rate of mortality is not that high or on the lower side, that is where one has to manage actively. And that's a very challenging situation. It's not easy at all. It doesn't die out. It cannot be ignored. Containing it is also very difficult. And most likely, the situation we have at this stage is fall under this quadrant 4. So I started with a praise for a simplification, simplifying, getting to the crux of the issue without getting into the details too much. And I would end with a caution that everything should be made as simple as possible, but not simpler, because in that case, we would lose some of the essence of that problem. That's all from my side this evening. This has been an appetizer, and the main courses will be served now. Thank you.
Thank you very much, sir, for your insightful and effective overview about our webinar in such a concise manner. Now I shall request Dr. Orijit Bag to introduce our first keynote speaker, Professor Sitavro Sinha. Before that, I want to make one request to all the participants. If you have any specific question related to the topic, kindly drop it in the question answer box, not in the chat box. We'll bring it up in the discussion session at the end of each lecture. Now, Dr. Bag, kindly introduce Professor Sitavro Sinha.
Thank you, Dr. Biswas. Good evening, everybody. It is my great honor to have an opportunity to introduce today's guest speaker, Professor Sitavro Sinha, who is a distinguished professor and a really true interdisciplinary researcher. His research works is traced across computational neuroscience to system biology, computational linguistics to mathematical epidemiology, complex system and networks to social and economic phenomena using statistical mechanics. He implemented nonlinear dynamics to pattern formation. His works was published in high-impact journals like Nature Scientific Reports, Physical Review, Physical Review, etc. He was graduated from St. Xavier's College of Kolkata in 1992 with physics honors. He did his master's degree in physics from the University of Calcutta in 1994. Then he moved to ISI Kolkata for his doctoral work and got his degree in 1998. After finishing his PhD work, he moved to ISC Bangalore, where he worked as a JNCSR research associate for a period of nearly 2 years, from 1998 to 2000. In 2000, he got AHA postdoctoral associateship in the and joined the division of cardiology of Wiley Medical College of Cornell University at New York City. Coming back from USA in 2001, he again joined at the Department of Physics, IIT Bangalore, as a PPISR Research Fellow, and then he joined the Institute of Mathematical Science of Chennai in 2002 as a Fellow E. At present, he is a Professor H at the same institute. With this small introduction, I welcome Professor Sina to this webinar and request him to deliver his talk. Please, sir, take over this webinar, take over this session. Thank you, sir. Professor, please take over the mic.
Thank you, Dr. Bug. Is my presentation visible?
Sir.
Yes, sir. Yes, sir, visible. Perfectly all right.
Okay. All right, great. Okay, so thank you for that, kind introduction. And
Sir, 1 minute. Can you make it in? Okay.
sorry.
Sorry, it's I just wanted to say that make it in the slideshow. So fine now.
Okay, sure. Okay. All right. So thank you for asking me to present some of our recent work on epidemic modeling. I chose to speak not specifically on COVID. Of course, some of the things I'll be talking about would obviously have application to COVID. So Professor Shamazdar has kind of anticipated some of the stuff that I'm going to talk about. But given that repetition never hurts, I would nevertheless still go through some of the fundamentals of mathematical modeling of epidemiology that he has already gone through. So, of course, COVID has brought the mathematical modeling of epidemiology to media attention like as it has never been before. While of course it's tragic, it has proved to be, a godsend opportunity for the field as such, because suddenly the mathematical epidemiology field finds itself very much in the forefront. So no need to remind those who are listening in that we are currently living through one of the fastest spreading epidemics in living memory. So, already as of last month, we had 10 million confirmed cases worldwide, and now the number is even higher. So what kind of strikes one when one looks at the numbers is how fast it has actually evolved. So the first report that there was something unusual going on came on the last day of last year, when a cluster of pneumonia cases were reported from Wuhan, China. Later on, it was determined that possibly the first human infection occurred around December 1. So, we are looking at about half a year, and already within that time, this epidemic has covered the entire world and has caused millions and millions of infections. So if we look at how precisely this act has played out, we could, for example, plot the number of active cases. So when I talk about active cases, I mean not the total number of people who have been tested positive since the time the epidemic began, but the number of people who are sick with the disease at a particular point of time. So that's precisely what I mean by active cases. So at any given date, the number of active cases is determined by taking the total number of confirmed cases and taking out the number of people who have died and the number of people who have already recovered until that point of time. So when I say number of active cases, please remember that I mean the number of people who are sick at that point of time. So what we find is that while it had grown extremely fast in the initial period, essentially the whole month of January, by February 17, by mid-February, it had seemed that we are seeing something like a turning point. So on that date, the growth of the epidemic seemed to have flattened out. So for a while, it seemed that just as the 2003 SARS epidemic, which initially had spread extremely fast, but was contained within a couple of months, at least worldwide, it continued to rage in Southeast Asian countries. But fortunately, we were spared the spreading of SARS in the rest of Asia and the rest of the world. So it looked like, similar to the 2003 SARS, we might have spared a worldwide pandemic. However, around March 5, 2020, the cases started increasing again. And of course, from that point onwards, we have just had an inexorable rise of the number of cases. Now, the reason for this non-monotonic behavior of the epidemic becomes discernible if we actually separate out the number of cases that were contributed by China and the rest of the world. So essentially, in China, where the disease originally arose, and for almost the whole of February, the bulk of the cases of the world actually came from China. There, the incidence of the disease, of course, continued to decrease even past March 5, 2020. So the reason that we saw that upward swing of the number of cases is because the rest of the world started catching up. In fact, by March 8, the number of cases from the rest of the world for the first time exceeded that of China. And of course, now China is not even in the top dozen countries with the highest number of confirmed cases. What about the situation in India? So, those who are keeping track of the news would of course know that we have now more than 1 million confirmed cases. So the first confirmed case, of course, occurred on January 30 when a student returning from Wuhan University to Kerala was found to have tested positive. They were quickly detected. The present rise in the COVID-19 cases actually dates from March 4th, when on a single day, 23 new cases were discovered, which included 14 tourists from Italy who were staying at a South Delhi hotel, and half a dozen family members residing in Agra of a person in Delhi who had already tested positive the day before. And subsequently, of course, we have had a sharp increase in the number of infected people. Because its effect has not been uniform throughout the country. So, if you look at the total number of confirmed cases, we find that Maharashtra essentially accounts for almost a third of all the cases in the country, and followed by Delhi and Tamil Nadu. But 8 states, Maharashtra, Delhi, Tamil Nadu, Gujarat, Uttar Pradesh, Rajasthan, West Bengal, and Madhya Pradesh, together accounts for actually 80% of all the cases. And furthermore, the trajectory that was followed by the disease in all of these states are actually quite different. So for example, Tamil Nadu initially showed a very rapid growth phase, but then towards the end of April, it had kind of flattened out. And for a while, the number of cases were actually decreasing. But then, of course, we had the Coimbatore cluster when suddenly, a large number of cases arose associated with the wholesale market, which kind of spread all over the state. And then we again had a very rapid growth phase of the epidemic, which continued for a few weeks. And then again, right now we have reached a bit of a plateau. Delhi, which had initially a very high rapid growth phase, has now achieved the distinction of having their growth rate negative for several weeks now. So they have effectively brought the epidemic under control. In Maharashtra, which has contributed for the bulk of the cases, it continues to rise, but of course at a much slower rate. So we find that it's not been exactly the similar kind of story within the country. So even though we might be analyzing numbers for the country as a whole, turning out the reproduction numbers and so on, one has to keep in mind that the same epidemic can actually evolve in very different manner in different regions, even within a country, even within a state, actually. But one question actually is true irrespective of what kind of trajectory you find the epidemic to be following. And that is, how do the numbers increase so fast? Essentially everywhere where the epidemic has broken out, we see this extremely rapid growth of the number of cases in the first few weeks. So for example, in Italy, the number of infected cases went from 20 on 21st of January to 453 on 26th of January. So that's a 20 times increase in just 5 days. So what is it that causes this very rapid growth in epidemics? And it turns out that it essentially is a wonderful illustration of a principle that every banker essentially knows, and which is this power of geometric progression, the power of exponential growth through geometric progression. So the geometric progression is the sequence of numbers that you get when you multiply something repeatedly by a constant factor. So imagine that initially at the very early stage of an epidemic, you just had one infected person. Now, that infected person infects 2 people before recovering. Now, each of those 2 people that were infected, each of them go on to infect 2 other people before they themselves recover. So at the second stage, we have 4 infected people, and then each of them infect 2 in turn. So at the third stage, we have 8 infected people, and so on. Now, initially, this increase seems like fairly mundane, but if you just continue this series, you see that it would grow from 1, 2, 4, 8, 16, 32, and very quickly to 64, 128, 256, 512, 1024, 2048, right? And very quickly you have, starting from a single case, 1,000, 10,000, and then 100,000 cases. All because every individual who's infected just goes on to infect 2 more. Now, of course, this is a simplification, because in reality, not every infected person will pass the infection on to the same number of people. Some would infect maybe 4, some would infect none. So we are talking essentially about the average number of people that an infected person infects. So for example, the figure that I'm showing here shows a possible evolutionary trajectory of a disease. So you start from a single individual is infected who passes the infection on to 2 others. Now of those 2, one of them recovers before being able to infect anybody else. So the chain of infection from this person essentially dies out. The other person infects only 1 other individual. So at that point, you would say that, look, the growth rate is just 1. Okay? So one single person is only infecting 1 other person. But then subsequently, this person infects 2 people, and then one of them infects 3, while the other one only infects 1. And then of these, for example, this individual recovers without infecting anybody else. This individual infects 2. This one infects 1, and this one infects 2. And so we can see that we can try to calculate the number of secondary infections that are caused by a primary infection and average it over all the individuals who have been infected. And this way we will, have a constantly evolving growth rate. So the initial phase of an epidemic, we can try to characterize how fast the epidemic is spreading by trying to calculate this initial growth rate. And this is the concept that lies behind a number that we have been hearing much through media outlets, the number called the basic reproduction number, or R0. Essentially, it's the number which tries to quantify how rapidly this exponential growth of the epidemic is happening. Now, of course, let me point out that it's not inevitable that when an infected individual enters a region which has had no cases, that automatically will lead to epidemic. In fact, at the initial stage of the epidemic, when you have very few infected individuals, it's very much kind of a chance events that actually eventually leads the number of infections to go up to epidemic proportions, because typically an infected person will come and would be, let's say, isolated rapidly and would not be able to infect anyone else before recovering. And so often at the initial stage of the epidemic, you would see, several such false starts when infected person comes in but is not able to infect enough number of people to start an epidemic. In order for an epidemic to actually start, you need to have this number to be greater than 1. Why? Because R0 is essentially defined as the mean number of new infections which is caused by a single infected individual. So obviously, if this number is less than 1, that means you expect that over time, the number of people who are infected would gradually just keep decreasing and the epidemic will die out. For the epidemic to happen, you necessarily need mean number of people who are infected by a single infected case to be greater than 1. And so that's why, we have, in the popular media, all this attempts or all this, great attention about what is R currently. Is it less than 1 or is it greater than 1? Because we know that if it is less than 1, then provided that this particular value is maintained, the epidemic is doomed to go away. One other point I'd like you to note is that R0 is strictly speaking a number which is valid at the initial stage of an epidemic, when the entire population is almost wholly susceptible. That is, you have not had some people who have already had the disease and are therefore now immune to it. It's only when the population as a whole is susceptible that we can talk about R0. If the disease already has had, a chance to infect many people in the population, so that some people are now immune to the disease because they had it earlier, then we have to talk about the effective reproduction number, which is called R. So why are we so obsessed about the basic reproduction number? Because it can actually tell us about how contagious the disease is, how rapidly would the number of cases build up, and different diseases have actually been, ordered in terms of their contagiousness by measuring the corresponding basic reproduction number. So for example, hepatitis C and Ebola, which actually differ quite a lot in their biology, their pathology, and so on, nevertheless are actually contagious to a very similar degree. Both have a basic reproduction number of around 2. HIV/AIDS has a basic reproduction number of 4. So does SARS. And in fact, coronavirus or the COVID actually also has a reproduction number which has been variously estimated between 2 and 4, but more about it later. Mumps, on the other hand, is a basic reproduction number of 10, and then measles has a basic reproduction number of 18. Now, the basic reproduction number, of course, does not say anything about how deadly the disease is. So Ebola, for example, which has a basic reproduction number of only 2, you might say, why are people so worried about Ebola when it has, one of the lowest reproduction numbers? Well, the problem with Ebola is that although it's not as contagious as, let's say, measles, it's extremely deadly. And so that is measured by a different number called the case fatality ratio, which essentially says that what percentage of people who are infected with that particular disease are likely to die. And for Ebola, this turns out to be, between 60% to 80%. So while for coronavirus, or while for COVID, for example, this number has been variously, measured to be about 3%. So, like if you have COVID, 100 out of 3 would probably die. But if you have Ebola, it's extremely likely that the person will die because, there's a possibility of 65% to 80% that this person is going to die. So that's actually slightly different from what R naught is actually all about. So how do I measure R naught? Well, usually what people do is they try to look at the empirical data and fit an exponentially increasing function. And then having estimated this exponential growth rate, they use the approximate relation between R naught and this exponential rate of growth and one other quantity, which is the mean generation interval of the epidemic. So this is basically measured as what is the gap between a person getting infected and the person from whom that person got the infection first showed the symptom of infection. So that's the period of time in which a person actually has chance to pass the infection on to others. So the longer that a person spends freely circulating in the population, spreading the infection around, obviously the higher would be the chance that the infection would be spread to many people, and so the higher would be R naught. So once we know the exponential growth rate, lambda, and the generation interval, we can actually, using this approximate relation, try to calculate the basic reproduction number from data. So we have in fact done this exercise for India, and where we estimated this R naught to be 1.83, which actually turns out to be pretty much at the lower end of the spectrum of the various R naught values that we have calculated for the different regions around the world where there have been significant outbreaks of COVID-19. So this picture, for example, shows along the vertical axis the 95% confidence intervals of R naught for various countries who are represented in terms of their 2-letter symbol. So for example, IT represents Italy, US represents, of course, United States, CS represents Spain, GB represents the United Kingdom, and so on. So India is around here. So you can see it's actually at the lower end of the different R naught values which have been estimated. But India is, of course, not unique. I mean, it turns out that most South Asian countries actually have had an unusually low value of R naught. So for example, this is Sri Lanka and this is Pakistan. The only exception turns out to be Bangladesh, which has had actually a pretty high R naught of around 3. Of course, we have all been pretty fortunate compared to Iran, which have had actually an R naught of greater than 3.4. So it's still not clear what exactly lies behind India's pretty low R naught. Could it be, some physical climatic factors? Could it be some genetic factors? The jury is still out. But the utility of R naught, I mean, why we actually try to estimate it as accurately as possible is because then from a public health policy perspective, we can actually use this to figure out a lot of things. So for example, you can estimate the final size of the epidemic if no control or intervention measures are taken to prevent the epidemic from spreading far and wide. So using a fairly simple implicit equation, you can figure out that if you have an R0 of 1.83 and there are no intervention measures like lockdown or anything in place, no vaccines whatsoever, then going by the theory, you would have probably before the epidemic ends about 74% of the population affected. Now, if a vaccine does become available, then what's the minimum immunization coverage you require to achieve herd immunity? So here also, there's a very simple relation involving R0, which gives you the estimate of what's the minimum fraction of the population you need to provide the vaccine to in order to stop the epidemic on its tracks. So, obviously the higher R0 is, the larger the fraction of the population you need to vaccinate. So for example, smallpox, which is of course one of the big success stories of vaccination, we have managed to eradicate smallpox simply by achieving extremely large vaccination coverage. So smallpox had a R0 of between 5 to 7. So you can work out from the theory that if you vaccinate between 80 to 86% of the population, world population at least, then essentially you would ensure that even though there might be localized outbreaks, smallpox would never achieve epidemic proportions. And the World Health Organization, of course, achieved this, a few decades back, and which is why we have managed to completely eradicate smallpox. Unfortunately, we have not been able to repeat this for other diseases. For example, for polio, this is a still ongoing effort. For measles, it turns out that you have to achieve, extremely high coverage, something like 90 to 94% of the world population in order to eradicate measles. So this has been a big challenge. Influenza, of course, has much lower R0, but there the challenge is different. It mutates, the pathogen responsible for influenza mutates so rapidly that a vaccine which is effective for the pathogenic strain for this season actually does not work for the next season. And so although, to achieve immunity against the influenza pathogen for a particular season, actually fairly easy to achieve, you only need to vaccinate between, less than 50% of the population. Nevertheless, this has not been a permanent success against flu. Now, for the estimated R0 of 1.83 for COVID in India, you can use this formula and that gives you, 45%. So that means if you vaccinate maybe half the population of the country, it should be fairly effective in achieving herd immunity. Now, the herd immunity actually brings to us a very important concept that I would be talking about in a few moments. And that's the concept of a public good. So from a public health perspective, herd immunity, achieving herd immunity is extremely important, because while the vaccine given to a particular individual can protect that individual, herd immunity means that even people who have not been given the vaccine can be protected from the pathogen simply on account of being hidden from the pathogen by a crowd of vaccinated individuals. Now, this is fairly interesting, right? So because you would have thought that in order to protect someone, that person needs to be vaccinated. Now, the surprising part is to eradicate the disease, you don't actually need to inject the vaccine to each and every individual in a country or each and every individual in the world. You only need to give the vaccine to a critical fraction. So how is it that the rest of the population gets protected? And that's essentially the power of herd immunity. So in herd immunity, what happens is, although you might have individuals who have not received the vaccine and are therefore susceptible to the disease, the pathogen would find it very hard to find such susceptible individuals in the population, because they'll be protected. The susceptible individuals will essentially be hidden by a screen of vaccinated individuals who are actually immune to the disease. And so it's a public good because those who are getting vaccinated, not only does the vaccination provide advantage to them, by getting vaccinated, they are also doing a social benefit because they are protecting the unvaccinated individuals from being exposed to the pathogen. So in a sense, being vaccinated is like, you are doing a service to the society, apart from, of course, also doing a service to yourself. Now, it might seem that this is all good, right? I mean, why wouldn't you get vaccinated? And in fact, the 20th century has been a success story from the perspective of public health, precisely because of the many successful vaccines which have been developed for a large number of diseases, which used to be fatal before, like diseases like chickenpox, measles, rubella, tetanus, and so on. And yet, we continue to see outbreaks of such vaccine-preventable diseases. So, for example, last year, the United States saw the largest measles outbreak in 25 years. So this is not, sub-Saharan country that we're talking about, right? I mean, there's no dearth of, public funding in providing vaccination coverage in a country like the United States. And this is not even true just for the United States. This is not that the United States is something very outlier or something. All over the world, we find that we have had cases of outbreaks of diseases for which vaccine is readily available. What's going on? It turns out that even in countries which has high vaccine coverage, individuals choose to either not receive the vaccine themselves or to prevent the child from getting the vaccine shot. And this, of course, creates an opportunity for the pathogen to spread. Now, this sounds very surprising, right? Why would you choose not to have a vaccine, in order to prevent either you yourself or your child from suffering from the disease? As Amanda Cohn, who's a senior advisor for vaccines at the American CDC, put the cause succinctly, there's vaccine hesitancy in a world where people don't see measles anymore. Okay? And of course, you can apply this for any disease for which vaccines are available. It turns out that the success that vaccines have met in preventing large epidemics of previously deadly diseases is precisely the reason for why people are hesitating to actually have the vaccines, because they feel that I'm protected, I don't have a very high risk of getting the disease, so why bother? Okay. So, but this is of course dangerous from a public health perspective, because as more and more people choose not to get vaccinated, thinking that the risk of contracting such a disease is very low, we have a growing population of susceptible individuals who are likely to actually form the nucleus of the next big outbreak of epidemics of such vaccine preventable diseases. So can we understand why this is happening through the use of mathematical models, and can that actually tell us about what we can do about it? So when we try to model it, we actually need to consider two very separate aspects of this problem. One is, of course, how diseases spread through contact. And in this, we model essentially how epidemics arise and spread through a social network of individuals in a population. And secondly, how do individuals take decisions to get vaccinated or to vaccinate their children? And for this, we need to model how individuals take decisions based upon information about the possible outcomes of their choices. So basically, they consider the risk of contracting the disease. They consider what's the possibility that they will actually get the disease, and how likely is it that if they don't have the vaccine, they can still manage to swing through. Now, going to the first part, how do we model the spreading of an infectious disease? How do we model an epidemic? It's an interesting point for us Indians to note that actually the earliest mathematical model of epidemic spreading was done by Ronald Ross, who's effectively the first Nobel Prize from India, because he got his Nobel Prize for his work on malaria done in actually various hospitals in India. And the first mathematical modeling of epidemic spreading was also done by him. Okay. Why? Why did Ronald Ross, who had already essentially world famous for his lab work on malaria, why did he spend time in working out the mathematical modeling of how epidemic diseases spread? Again, that has got to do with his effort to eradicate malaria. So Ross essentially had argued, based upon his work, that in order to control malaria, the key is to control the insect population. Now, although it seems fairly obvious to us at this point of time, at the time when Ross was talking about this is the first decade of the 20th century, the popular wisdom was that, look, it's impossible to completely, make malaria population zero. So you cannot make the mosquito population extinct. And so therefore, it's impossible to eliminate malaria by controlling the insect population. So Ross had to convince people somehow that, look, even if you manage to reduce the mosquito population by a fraction, it would have an immediate perceptible effect in the malaria spreading. But how would he do that? So initially he tried to do that by creating, doing experiments in controlled conditions. So he would go to, for example, certain places and, initiate mosquito control programs. And then, he would try to show that, look, the number of cases are actually coming down. But this was extremely time consuming. It takes several years to control a mosquito population to the point where you can actually see a significant decrease in the number of malaria cases. And very often, after a year, the government would lose interest and would pull out funding, and Ross would be left with very little to show for all the effort he had put in. So he turned to mathematical modeling. So essentially he wanted to answer the question, is it possible to control malaria even if you have not removed every single mosquito? And so this is how he argued. So he said that, look, let's say you have a place where there are about 40,000 mosquitoes, and let's say only 1 in 4 mosquitoes manage to bite a human. And so therefore you have about 12,000 mosquitoes which bite humans. Now, essentially, let's say you have only 1 human in a village of 1,000 who are infected. And so, a mosquito would, contract the parasite. Mosquito will get that parasite only if it manages to bite that particular human. So that means out of this 12,000, on average, only about 12 mosquitoes are going to bite that infected human. Now, let's say only 1 in every 3 mosquitoes survive to become infectious, because it will take some time for the parasite to actually go through the various stages where it eventually is able to transmit itself through the mosquito's mouth. And so let's say 1 in 3 of 12 means 4 mosquitoes survive to be infectious. And then since only 1 in 4 mosquitoes manage to bite a human, you'd only have 1 infected mosquito which bites a human. So this makes it pretty clear that even though there are about 40,000 mosquitoes, it eventually translates to actually very few infected mosquitoes which are biting a human. And so if you manage to control mosquito population to a manageable number, you should be able to eradicate malaria. So this is what Ross kind of translated it as what he called his mosquito theorem, namely that malaria cannot persist in a community unless the anopheline, the mosquito species which were actually spreading the pathogen, are so numerous that the number of new infections compensates for the number of recoveries. Now, this is a crucial insight going much beyond the specific context of malaria in which Ross actually mentioned it. So you would have a process by which the number of new infections are occurring. So, infections, infected people are essentially causing more infections, but it also have infected individuals over time either dying and therefore removing themselves from the population or recovering. Okay? And so you have to have these two processes balance each other. So if it turns out that there are more recoveries than new infections, then you can actually eliminate a disease. And this was actually a crucial insight. And this was generalized from beyond malaria, which was, of course, a vector-borne disease where actually the pathogen is spread by an intermediate organism, to diseases which spread by direct contact, like for example, influenza or COVID-19. And this led to the class of epidemic models, which actually we use very frequently these days. The SIR model, which Professor Shukla kind of mentioned at the beginning of this meeting. So in such compartmental models of epidemics, what we do is we assume homogeneous mixing. That is, anybody in a population is equally likely, upon their getting infected, to infect anyone else. So we divide the entire population of individuals into three categories. One are the susceptible individuals who have not got the disease but are likely to get infected and have the disease. The compartment of infected people, or I, so these are people who currently have the disease. And finally, the category of people who have recovered or are removed through death. So people who have had the disease and either died or had the disease recovered and so therefore are immune to the disease. So how do you move from one compartment to another compartment? So let's say you are a susceptible individual. So you can only get the disease if you come in contact with an infected individual. At that point of time, with some rate beta, you are likely to contract the pathogen from the infected individual and become infected yourself. And so that's what is meant by this reaction shown over here, that upon the contact of a susceptible and infected individual with a rate beta, you have two infected individuals. Now, if you're infected, after some point of time, you either recover or get removed through death. And this is also happening through some rate gamma, which is actually the reciprocal of the average period over which you remain infected. So this is the reciprocal of the average infectious period tau. So gamma is actually 1 over tau. So this idea essentially was first pioneered by two mathematicians working at Edinburgh University, McKendrick, who was actually a protege of Ronald Ross, and Kermack, a chemist who was working at Edinburgh University, who happened to lose his eyesight because of a laboratory explosion, switch his interest to mathematical modeling because he couldn't work in the laboratory anymore. So the two of them collaborated and came up with the SIR model in 1927, which essentially gives you the mechanism by which you can actually say at each point of time what would be the number of people who are infected and the number of people who have recovered. So how do you do that? Well, you have essentially three equations, one telling you how the size of the susceptible population changes, one telling you how the infected population size changes, and the other telling you how the recovered population changes. But since the total population of susceptible plus infected plus recovered is a constant, you can essentially use the idea that, look, since S plus I plus R is a constant, then only two of these are independent equations. And so I need to only work with two independent equations. So here I'm only going to talk about the two independent equations, namely the change in the susceptible population and the change in the infected population. So how does the susceptible population change? Well, it changes when you have a susceptible individual meeting an infected individual who then passes the infection on to the susceptible individual. So the susceptible individual now goes to the infected category. So over time, you can only have the susceptible population size decrease as more and more of the individuals in that category go on to augment the infected category. And so that's why you have a minus sign over here, because the change is only negative and it's proportional to the total susceptible population size and the total infected population size times, of course, the rate at which susceptibles are becoming infected on contact with the infected individual. So you have ds dt equal to minus beta into S into I. What about the change in the infected population? That is affected by actually two processes. The infected population size increases because as a susceptible person becomes infected, that person joins the infected population, thereby increasing the infected population size. But you also have a decrease of the infected population because as people recover, they leave the infected population category and join the recovered population category. So you have a growth through new infection and a loss due to recovery of sick individuals. And so you have essentially a term which is essentially identical to the term that we had on the right-hand side of the DSDT equation. So this basically tells you what's the increase in the infected population because of fresh infections. But now you also have a minus the term which is proportional to the current infected population times the recovery rate. Okay, so you have minus gamma into I. So now you have a very simple equation, dsdt equal to, or didt equal to beta si minus gamma I. Now, for an epidemic to be occurring, you necessarily need the number of infected individuals or the size of the infected population to increase over time. So that would mean that you have to have the change in infected population to be. Now this is positive, and you can easily work this out mathematically. If didt, which is equal to beta into s into I minus gamma I greater than 0. So very simple algebra will show that at the initial stage of the population, S should be greater than gamma by beta. That is the initial susceptible population size, which is actually equal to the total population size, because you remember at the initial stage, almost the entire population is susceptible. And so if you say that S at time t equal to 0 is simply N, it means that the N has to be greater than the ratio of the two parameters, gamma and beta, for the epidemic to occur. Now, it turns out that there's a very intimate relation between the basic reproduction number and these quantities. So it turns out that R0 is nothing but N times beta by gamma. And since gamma is simply 1 over tau, the average period of infection, you can actually write R0 as N beta tau. And from the condition that N has to be greater than gamma by beta for an epidemic to occur, you can very easily show, so for an epidemic to occur, N beta tau has to be greater than 1, but this is nothing other than saying that the basic reproduction number has to be greater than 1, which we already had seen earlier. So Kermack and McKendrick's model actually very simply explains the fundamental mathematical aspects of how an epidemic develops over time. We can, of course, make this much more sophisticated by introducing additional compartments of exposed individuals who don't show the disease for a while after getting infected and so on. But this forms the basic model on which all such details are kind of incorporated. Now, I had mentioned that one of the assumptions of the compartmental models is that of homogeneous mixing. That is, people are equally likely to infect one another. But of course, in reality, the kind of social relations we have and the physical proximity or geographical proximity that we have with other people makes it more likely that we're going to infect some people rather than others. So for example, you're much more likely to receive an infection from your family members or from your office colleagues rather than with some arbitrary stranger somewhere else. So this means that we need to consider both the role of our social network contact structure as well as the role of space when trying to understand how real epidemics spread. And so this is why, currently with, the existence of many ways to gather information about our social network, interest has focused on understanding how epidemics spread on our social networks. So if we have the contact structure of a population, who actually comes in contact with who on a regular basis, we can actually model the epidemic spreading on a social network. So we essentially have to see this as a network, and essentially a network or a graph is any structure which can be divided into a set of nodes or vertices. So these are represented by the circles over here and the links between them. So these are the physical contacts, and this together defines a network, and it's usually mathematically represented by what is known as an adjacency matrix. So the inner matrix, each component, the ijth component of a matrix is 1 if a link exists between I and j, and it's 0 otherwise. And in our particular case, each vertex is an individual. Each link or interaction is a physical contact which allows contagion transfer. And the system is, of course, the population over which the epidemic spreads. So for example, using this kind of formalism, we can model the progress of epidemic in real populations. So this, for example, is the social network of a village in southern Karnataka, for which we have obtained the information from an NGO, which collected the information for some other purpose. So if you simulate a disease that spreads to this population, you can actually see how through the social contact network, the epidemic actually again and again recurs to the population as people essentially contract the disease, get infected, recover, and then become susceptible again over time, and then again contract the disease. So this tells us that actually incorporating the network structure can tell us many facts about the disease which would have been ignorant otherwise. So for example, one of the things you note is that this population is organized into strongly clustered kind of structure. So there will be groups or communities of people who only mostly interact with each other. And there will be very few interaction between, for example, different communities. Now that turns out to have a very strong impact on how an epidemic spreads to that population. So the existence of such community structure means that a disease which has extremely high R0, which in a homogeneous population would have just quickly swept through the population, infected everyone at one go, and then just died out, can actually stick around for extremely long times. So one of the big mysteries of epidemiology had been that why is it that extremely or highly contagious diseases sometimes can be surprisingly persistent? They can last for several years. So people had assumed that maybe there was a animal host in which the disease was lying around and then came back every season and so on. But it turns out that there might be a much simpler explanation. It has to do with the way that our populations don't have everyone equally likely to contact everyone else, but we tend to form these kinds of communities in which we have very strong interactions with members of our own community, but very few interactions with members of other communities. So that kind of a population structure is actually conducive to making highly contagious diseases strongly persistent. Now, how do we model the vaccination behavior in such a population? So, we have, as I said, populations divided into 3 categories: susceptible, infected, and removed. So a susceptible individual goes to an infected category upon infection, and then the infected individuals go to the removed category upon recovery. But you now also have a possible jump directly from susceptible to removed category through vaccination. And that's because a removed category essentially means a person who is immune to the disease. So that can of course happen because you got the disease and you recovered, so that now you have the antibodies, but it could also be because you didn't have the disease, but you just had a vaccine shot. Now, we can actually model very efficiently this kind of a epidemic model with a vaccination put in, but we are missing one very important component. We have the disease transmission part of the model, but what about the vaccination decision model? How do people decide whether to get vaccinated or not? So assuming that agents are rational individuals who are trying to maximize their personal utility or benefit based on all the information that is available to them, we can actually use the mathematical theory of games, which describe how people strategically take decisions. Now, of course, the theory of games has been around for almost a century now, and its antecedents goes even further. So essentially, when I say games, I mean strategic interaction between agents. And agents in the context that I'm talking about would of course be individuals, but in general, it could mean anything, an organization, nation, or even a computer program. Each agent typically receives a payoff depending upon the choice of strategy of that agent as well as of all the other agents who are playing against that particular agent. And essentially everyone tries to maximize their payoff, maximize their benefit by choosing an optimal strategy. But of course, here you have to take into account that the others are also taking strategic decisions, and you have to take that into account in your decision making. And the classic way of viewing such a game is in terms of two individuals playing a game with each other, where each has a choice of two possible strategies. We call them action 1 and action 2. Now, depending upon what action that each individual takes, you get a particular payoff. So for example, if both agents take action 1, then both receive a payoff of R. If both choose action 2, both receive a payoff of P. Whereas if one player chooses action 1 while the other chooses action 2, then the one who had received action 1 receives S, and the one who chose action 2 receives T. Now, this might seem very abstract and so on, but I'll give an example of how this actually is extremely important to understand a whole set of very practical situations. Now, game theory was, of course, brought to life by John von Neumann in collaboration with Oscar von Morgenstern, but it received an enormous boost by the discovery of the concept of Nash equilibrium by John Nash in 1950. So essentially, Nash gave a prescription for how to come up with a solution. What is this optimal solution, or what is the optimal strategy for individuals if you have the payoff matrix given? So if you know the game, what should be your optimal strategy? And Nash gave a formula for that. Now, let me give an example of such a game. So this is one of the most well-known games in the literature of two-person symmetric games, and it's called the prisoner's dilemma. Imagine that the police have arrested two people who are found in suspicious circumstances, and they want to pin some crime on them. Now, in true Hindi film fashion, they put each of these individuals into separate prison cells and interrogate them separately. Now, the only hope of the police to actually, implicate them is to have them confess, okay? Because they don't actually have any concrete evidence. So how do you make a person confess? Well, you try to threaten the person with dire consequences if they don't come clean. So to each person, the police say that, look, if you decide to confess, then if the other person doesn't confess, you immediately go free. Whereas if both of you confess, well, you get some minimal jail term. But on the other hand, if you don't confess and the other person confesses, you are in for 20 years, let's say. Now, from the point of view of each person who's being interrogated, what's the best option? Should that person confess or should that person remain mum? Okay. So you can frame this in terms of a payoff matrix, where you say that each of these individuals, A and B, have two possible options: cooperate, that is to remain silent, and defect, that is to confess. And based upon what the other person does, and they have no way of knowing what the other person will decide because there is no communication in them, based upon what the other person does, they have various payoffs. So if both persons decide not to confess, they decide to remain mum, they get a reward for cooperation. So what's this reward for cooperation? Well, essentially, let's imagine that the police really don't have anything to put them in jail for a long time. So after a month, they have to let them go. So if they both decide to remain mum, the police keep them locked up for a month and then let them go. However, if both decide to confess, then of course the benefit of a single person's testimony is diluted, and let's say both go to jail for a year. Now, the interesting question, what would happen if one person confesses and the other person doesn't? So then, of course, the person who confesses becomes the state's witness, and the person who didn't confess becomes the murga and goes to jail for 20 years. for a crime which possibly he didn't even commit, right? And so the sucker's payoff, okay, the punishment that you get for being the good guy is actually the worst in this case. Okay, so that's why we have this order of the various payoffs. So the best payoff is if you decide to be the bad guy, the other person doesn't confess and you confess, then you get the best of all possible outcomes. You immediately walk free. The next best option is if you both decide to remain mum, in which case you just go out after remaining in jail for 1 month. The next best option is the penalty for mutual defection, where you both confessed, and so the value of your individual testimonies becomes diluted. So let's say you each went to jail for 5 years. But the worst possible outcome is, of course, the sucker's payoff, where you go to jail for 20 years while your colleague kind of walks free. Now, let me just tell you the answer in terms perspective of Nash. So Nash solution is that given this scenario, you should always choose to confess. But the problem, the kicker is that, of course, your opponent, the other person who's in jail with you also has exactly the same idea, right? He has also read Nash, he also knows game theory. And you will say, oh, okay, so I should confess. So both of you decide to confess, and you actually end up with the reward P, which means each of you go to jail for 5 years. If you weren't so smart, and if you just had basic, decency, both of you would be good people and say that, okay, we won't, snitch on the other guy. We will remain mum. And so then you would have ended up with R. You would have, walked free after a month. And so this provides a dilemma, right? Being extremely rational, being extremely individually rational, trying to figure out what's best for yourself, being so selfish actually can end up in both of you being in a worse situation than if you had been not so smart, not being so rational. Now, you can also have other kinds of games where you kind of, flip the ordering of these payoffs. That, for example, one of these possible orderings gives you the game of hog, dove, or chicken, which has been used to, for example, model mutually armed destruction in nuclear armed individuals. And here it turns out that the Nash solution is very different. In fact, there are different types of Nash solutions, which include, pure strategies where one person defects and the other person cooperates, or a mixed strategy where each with some probability decides to defect or cooperate. So we can use game theory to understand vaccination decisions, where the players are the individuals who are deciding whether to vaccinate or not. So the action is simply whether to vaccinate or not to vaccinate. And the payoffs are essentially decided by the risk, perception of how likely they are to get infected, and the cost of getting vaccinated. Now, when I say cost, it does not necessarily mean monetary cost. It might also mean the fear of side effects. So, for example, you may not want your child to get a vaccine if you have heard some rumor that this might make the child more likely to develop autism. Okay, whether true or false, we are not getting into it. But you'd say, okay, no matter how slight this chance, I'm not going to take a risk because anyway, the child is protected because everyone else's child is getting vaccinated. So it's very unlikely that my child is going to contract the disease. So I'll just play safe, let everybody else's child get vaccinated. My child won't get vaccinated. So since I'm running out of time, what I'll do is I'll just show you quickly the structure of the model. So essentially we do a two-step process in which we first model the epidemic propagation where people get infected and people get recovered. And then this essentially results in a updating of the payoff matrix of each individual, using which they're deciding whether to vaccinate themselves or not. We can actually work out the Nash solution corresponding to that payoff matrix. And this actually tells us what is the probability of each individual of taking a decision whether to vaccinate or not. So based upon this probability, the individuals are getting vaccinated at each point of time. Now, how is it that the people get the information about whether they are likely to get the infection? So this is the place where we kind of consider the information that people use to decide how likely they are to get infected. So they could be using entirely local information, or they could be using entirely global information, or it could be some mixture of both. So here, that's kind of a parameter we use, alpha. So alpha basically tells you what is the nature of the information that people use to take decisions about vaccination. And using this, they then take decisions through this use of the game theoretic apparatus. So again, we have done the simulations on the various social contact networks of Karnataka villages. We have about information of about 75 villages. So you carried out this simulations on these real social networks. And what we find is actually that the success of a vaccination program crucially depends upon the nature of information that people actually use to take decisions. So obviously this also depends upon the contagiousness of the disease. So here what you see is on the horizontal axis, we have the contagiousness of the disease measured by the quantity R0, the basic reproduction number. Along the vertical axis, we have the eventually how much fraction of the population were infected and what fraction of the population were vaccinated. So you notice that in both situations, the population which were using purely local information, alpha equal to 0, had a much lower fraction of the population infected than the population who were using global information. Now, when you come to the fraction of people who were getting vaccinated, you find something very surprising. You find that there is kind of an intermediate zone of R0, intermediate contagiousness of the disease, for which actually people who are using global information would have more people getting vaccinated than people who are using local information. But that does not reflect in a lessened burden of the disease. Now, this may appear surprising, right? Why is it that more people are getting vaccinated, but that does not mean that there would be less people who get infected? That's because here we are seeing a situation of too much, too late. So people using global information are essentially receiving information about the deadliness or the contagiousness of the disease only once you have a critical fraction of people having already gotten infected, and then they rush to get vaccinated. But by that time, it's already too late. The infection already has, completely permeated through the entire population, and it doesn't really matter what action you take. By contrast, people who use local information actually are doing the right thing at the right time. It's like the Japanese Kanban principle, exactly the right amount at the right point of time. And that's because they're actually responding to their changing circumstances in their immediate environment. So we have looked at not just real social networks, but also model social networks. And we find that the results apply even in model social networks. So it's not really crucially dependent upon the intricate details of the social networks that we're using. It turns out to be only depending upon the average number of contacts per individual. It also holds true no matter what system size, what population size we take. It turns out that there is a very sharp change from low vaccination coverage to high vaccination coverage as the contagiousness of the disease increases. Whereas if you're using global information instead of local information, this happens to be much more continuous, and actually that leads to very different outcomes in terms of the success of the vaccination strategy. So to conclude, understanding vaccine hesitancy is of course extremely important, because this can potentially reverse all the success that 20th century public health programs have achieved by eliminating various diseases. Paradoxically, the success of vaccination program is precisely what has led to vaccine hesitancy, because as the incidence of a disease comes down, people are less and less willing to go and vaccinate themselves, because they have perception that they are not that much at risk of getting the disease. So what we have done is we have modeled this by a kind of a model which combines epidemic spreading on social networks with individuals on that network taking strategic decisions whether to get vaccinated or not. And we find that the decisive factor which affects how likely people are going to take the vaccine is the source of information that people use to find out how prevalent the disease is, whether they use local information or global information. So we find that a much higher vaccine coverage is observed when individuals compute their risk based upon their disease prevalence on their local network neighborhood, as opposed to global information, which, for example, is obtained from mass media. Okay? So for this, at least it turns out that talking to our neighbors is much more helpful than actually listening to the TV news. And the results are independent of population size, what kind of networks we use, and so on. But of course, it depends strongly on the average number of connections per individual. So I'm extremely sorry for running way out of time. I'd like to thank all of you who have listened so attentively to the talk. If you are interested in reading more about it, the paper was published last year in PLOS Computational Biology. And I'd like to conclude with the cartoon was shown over here, which shows that, of course, this is a concept that even a 6-year-old can understand. So thank you.
Thank you, Professor Sinha, for your mesmerizing and excellent talk. I'm confident that every participant of this webinar must have some important knowledge from you. Your talk particularly because everywhere there is a talk about the herd immunity from the beginning of the COVID pandemic, and but people are not actually aware what is herd immunity. But your talk explained all these things, and the another important thing I must mention the about the strategies of vaccination, because all are anxious about the when the vaccine will come, but not only the vaccination, but that is proper vaccine will come. You need the proper strategy for the vaccination to stop the pandemic, and you talk cover all the details of these things, and obviously your mathematical details about the pandemic and a lot of stories behind the malaria and Ronald Ross. So it is an excellent talk, and we have lot of questions. Few questions are in question answer box, but few are in chat box. So I think better we start from the question answer box, and then we, because in chat box there are a lot of noise as there, so difficult to extract all these questions. But start from the question answer box. So first question is by Sudhi Chaudhary. His question is: can you unified patient information data in India can control an epidemic or pandemic situation to identify the trend and migrate it through, probably it will migrate, I don't know, migrate through some statistical model. Sir, if you are familiar, you can go also to the question answer box to see the question. I will only assist you. It will be, I think, better to understand for you.
Okay, so first of all, I think the important point one should note. Sorry.
Yeah. Sir, I'm not getting your voice, sir. So now it is coming.
Hello.
Hello, yeah.
Orijita, you please read out the question one by one and convey to the
Yeah.
convey the
Sorry. Can you hear me?
Hello. Yeah.
Professor Sinha.
Your voice is not coming, sir.
Okay. I can see the question. Let me just answer the first question. So the question was, can a unified patient information data in India control the epidemic situation to identify the trend and mitigate it through some statistical model? So the point I hope I could carry across is that one of the things we are looking at is the high diversity trajectory of the epidemic dynamics in different parts of India. Am I
Hello, sir. Probably there
Yeah,
is some.
am I audible?
Yeah, now you are audible.
So to answer the first question,
Yeah, there's a network problem is there.
hello.
Yeah. So you are audible,
Hello.
hello, sir. You are audible, sir, now.
Yeah, yeah, yeah. Okay. So I was saying that the first question, which said basically that can unified patient information data in India control the epidemic situation? Uh, I mean, that is already available, this information data.
Hello, Abrasina sir,
Sorry,
your
it
voice
seems
is
the
not audible.
connection seems to be fairly unstable. It's
Yes, sir.
constantly switching off.
Yeah. It's difficult to continue.
Hi, the connection seems to be fairly unstable.
It's coming and going like that.
Hi, yeah. So the connection seems to.
Yes, sir. Going and coming. Connection is not stable.
Sir, we can hear you. Please carry on.
Yes, sir. You can.
Or maybe we can have the question answer session at the end together, if possible.
We can merge the two discussion sessions after the second lecture. That we can do.
Yeah, because
Hello?
very difficult.
Sir, if there is any network issue,
So I will actually.
Again,
I will try to type the answers in
okay, sir.
the chat, in the
Yes.
question answer box, because it seems the.
yeah,
Yeah, that will be better, sir. If you can, that will be our very nice. Or other or otherwise, we can repeat these questions in the second discussion session also. So, can we move on to the next lecture session?
already.
Yeah, I will type the answers in the question and answer box.
Okay, sir. Thank you very much.
Thank you, sir. Thank you, sir.
So, we move on to the next lecture
Yeah,
session.
I will just type the answers in the question and answer box. Okay.
Hello?
Hello.
We are move on to our next speaker. Our second speaker is Professor Molay Banerjee from IIT Kanpur. He will talk about multi-scale modeling of COVID-19 pandemic situation. I will request Dr. Taposh Ghosh kindly to introduce Professor Banerjee. Please, Dr. Ghosh.
Thank you, Dr. Bishar. It is a moment of pleasure for me to introduce such an renowned mathematician at IIT Kanpur. So, Professor Mola Banerjee did his PhD from University of Calcutta in 2005. He served Scottish Church College as lecturer for the period of 7 years before joining as an assistant professor at IIT Kanpur in 2008. Presently, he is a full professor at Department of Mathematics and Statistics at IIT Kanpur. Now, his research interests focus on mathematical ecology, eco-epidemiology, nonlinear dynamics, spatiotemporal chaos, and pattern formation. Dr. Banerjee has published more than 140 articles in reputed international journals, as evident from his Google Scholar citations, which reveals his H index of 27 and ITEN index of 60. He has also been associate editor for 2 special issues on COVID-19 modeling for the journals of Mathematical Modeling of Natural Phenomena and Letters of Biomathematics. Now, with this very brief introduction, may I request Professor Banerjee to deliver his lecture, please.
Thank you very much. Let me first share my screen and then I'll start.
Sure, sir.
Can you see my screen clearly?
Yeah, it's visible, sir.
Can you see my entire screen?
Yeah, it's the full screen, sir. Please.
Okay. Okay. Thank you very much for a kind introduction and also invitation to deliver this talk. It is a good opportunity for me to be the second as well as last speaker, because most of the terminologies are already explained by Shithabroda, that is Professor Shithabro Sinha. So it somehow make my job little bit easy. So at the very beginning, I must say what Professor Sinha has said, I'm going to talk about more or less in a similar way, but the same approach in terms of ordinary differential equation and coupled differential equation, and I'll try to give you some another new approach that is called multi-scale modeling in the context of COVID. At the same time, I must confess, or I must mention that there are various types of modeling approaches. Most of them are successful. So if the question arises that instead of this modeling approach, if we follow something else, you are always welcome. So in my talk, what I am going to present, that is my own thought about this appropriate modeling. And in the consequent time, I will explain why I am quite inclined or in favor of this appropriate or a particular type of modeling approaches. So this is the overview of the things what I am going to talk here. So although you are familiar with all these terms and these are the known pictures, we are a little bit bored about these pictures for last 4.5 months. So let us move on to some sort of insights for COVID epidemiology. So these are some extracts that I have collected from Worldometer's data. It is available. The link is given at the top. So first of all, as of 22nd July, you can see this is the list of the name of the countries who have recorded, as of now, highest number of reported cases. Those are mentioned in the second column. And the third column, it indicates the total number of deaths so far. So in order to understand that how severe is the disease in different countries, these particular numbers or metrics are important, but there are many more things that we need to give emphasis in order to understand the complete picture. So for that, what we can do, from here, one can try to estimate, okay, what is the percentage of number of deaths compared to total number of cases. That is one aspect, but you can look at some different aspects also. The point is that in terms of total cases and total deaths, we have a list of countries here, but keep in mind the ordering of the list of countries as of now is according to the descending order of total cases. So if you rearrange these country names in terms of total deaths, so there will be some sort of rearrangement. With this one, now if we incorporate the number of critical cases, then you can see that now India is at the second position. It took over Brazil, and Brazil goes down to third position, and there is some sort of alteration. Although I have mentioned here that data as of 22nd July 2020, but believe me, I checked this data for last couple of days, and if I recall correctly, from 20th July and onwards, there is no update about the number of critical cases at the website Worldometer. Of course, you can find some other repository where you have some other collecting method of data from where you can recheck whether these data are correct or it needs some sort of alteration. Next, if we go to the another parameter, that is what is the total number of active cases as of now. So then you can see that number of active cases more or less maintaining the same ordering as the number of total cases. So from here, what we can infer that probably the rate of recovery in all these countries are more or less same or maybe close to each other, but we need to take care of some different aspects before claiming that these are maintaining the same ratio. Another important aspect for this kind of COVID epidemic is that once we are talking about total cases, just purposefully I have written total cases instead of writing total infected. It may happen there might be some sort of underreporting cases, there might be some undetected cases. Rather, precisely what we can see that these many number of people are tested to be positive in these countries. Then the question is that what is the rate of the testing? If you look at the rate of the testing and arrange in the highest number of tests per 1 million, you are surprised to see that none of those country names are appearing in this particular list. So maximum number of tests per 1 million people per 1 million is done by Monaco. But another surprise is waiting for you in the next slide, that you can see what is the total population in that particular region. So if you look at that, Monaco is total population is less than 40,000. And if you look at the Worldometer data, as per Worldometer data, they have tested more than 38,000 people. And among these 10 countries who did maximum number of tests per 1 million, among them, Falkland Island is already declared as free from COVID as of now, because during last 24 days, there is no reported positive cases so far. So that's why purposefully I have marked these things in a green color. So why I'm talking about all this data here? I'm talking about all this data is only for the reason because my main target is to talk about multi-scale data. Multi-scale model. The multi-scale model, what is the basic idea? The basic idea is that if you look at the data from different locations, then you can see a variety of variation or continuous variation if you look at the data continent-wise or certain region-wise or country-wise, state-wise, district-wise. There are so many variations. And in order to have a clear-cut picture of a particular region or particular state or a particular country, towards the end, I'll try my level best to make it clear that why multi-scale modeling is very much important. Because size of the population, their interaction, these are equally important in order to have a better estimation. So now if we look at some sort of data as per different segregation. So first we talk about data that we can see from 6 different regions as per segregated by WHO. So from now and onwards in next slides, I'll use the shorthand notations, that is WP for Western Pacific, US for America, EU for European countries, and so on. So what we can see, that first case was reported, all of you know that it was in China, and that's why in this case you can see the growth in number of reported cases from 17th January to 31st January of 2020. So this is the daily number of reported cases in the region Western Pacific. Now within the same graph, if we incorporate the data from other regions, so within this scale, these are more or less negligible. You may presume that there is no such variation from other regions. But if you have a close look, then you can see that some sort of variation is observed. But the point is that daily number of reported cases as of 31st January in the remaining of the region remains below 10. As Professor Sinha has said, that initial exponential growth rate is an important factor. This is really an important factor, but the point is that you need quite patience you need to maintain in order to understand from where we should calculate this initial exponential growth. Another important thing is that looking at the data, you can clearly understand that as per this region, their initial exponential growth rate are completely different, but not for this slide. I'll come to that slide later. Now, if you look at the data from these 6 regions up to 31st of March, and then you can see that Western Pacific and Southeast Asia, they are maintaining the daily reported cases much less compared to US and Europe. I purposefully incorporated this slide here just in order to convey one message that up to 31st March, the daily reported cases from US was much less compared to total European region. And then if you look at the data up to 22nd July, then you can see that US is well ahead of daily reported cases compared to other regions. And these are raw data. So that means daily reported cases I have collected from there, and then I plotted in MATLAB just to produce this particular picture. Now, if you look at the cumulative number of reported cases, so it shows that different growth rates, these are now apparent from this particular picture. So if we consider, or if we want to fit some exponential curve against this cumulative data, then you can clearly understand that there must be some different exponential growth rates in order to have the best fitted curves corresponding to this data set. And now if you look at this particular data set, not over the entire range, but over a shorter range, and if you use some sort of 7 days moving average, and then you can understand that initial exponential growth rate for these regions are completely different, and using the appropriate technique, you can calculate this initial exponential growth rates. So with respect to 6 different regions, there is different growth trend, growth rate, and as well as total number of cases. So if we look at different regions, so there is some sort of remarkable difference that you can see out of these particular figures. Now, once we need to work on data, at the same time, we need to be very much careful whether data is good enough or not. If you look at the data for European region from WHO, their website, then you can find that one day, just after 30th June, they have reported more than 10,000 negative data, because there was some sort of under-reporting or over-reporting. Those they have adjusted, and that's why we can see a downward peak, which is touching more or less minus 10,000. And if I recall correctly, this is 10,000 something value they have reported on that particular day. And this one is somehow indicate us that instead of considering daily reported cases, we can think about some sort of 7 days moving average in order to overcome the situations that during the weekend there will be less people will be available for working at the workplaces, and there might be some sort of under-reporting. And afterwards, I'll show in the case of Brazil, this is clearly visible if you look at the daily reported cases. And now for these European data, if you consider the 7 days moving average in order to smoothen the data that you have here, still you can see here some kind of surprising behavior that you can observe, and that is due to that negative value that you have observed in the previous slide. But the one beneficiary point is that instead of having some negative value, if you consider the 7 days moving average, now each of these values are now positive, and except for this small domain, it more or less gives us some sort of trend that we can try to model with the help of some sort of mathematical equations. But if your final fitting does not matches with this data, there is no need to worry. Maybe you can use some other technique, or you can try to fit this data starting from this point up to this one, and then you can extrapolate it and then continue. So there might be some sort of mismatch at this particular range. Now, if we look at the data from country-wise, earlier we were talking about region-wise. Now, if we talk about country-wise, then in this particular table, what I have listed that days on which the total number of reported cases was 100, 1000, 10,000, and so on. So in case of China, below 1 lakh, I have mentioned the date 22/7 in red color only for the reason that till today, their total number of reported cases is below 1 lakh. And again, for these countries, that Italy, Iran, France, Germany, UK, still they maintain the total number of reported cases as of now is below 5 lakh. But other countries, they already, like Brazil, India, Russia, they crossed this particular checkpoint of 5 lakhs total reported cases. And from here, what you can see, that number of days it required to move from, or getting multiplied from 100 to 1000, 1000 to 10,000, 10,000 to 1 lakh, and so on. These are significantly different if you go from one country to other country. And once you represent these things in a pictorial manner, so then you can see here you have one slope that is moving from 100 to 10,000. Then another slope that you can observe here. So that means there is a rate of change from this particular range. And afterwards, it more or less maintain the same slope, because after that, there is no such change is observed here. But if you look at these particular curves for other countries, you can see lots of different kind of variation. So with China now, if you incorporate the data for Germany, so again, you can clearly understand that this particular trend is significantly different from the trend that we have seen from China. And now if we incorporate other countries like France, UK, Italy, Iran, India, each of them, they shows different kind of trends. And from here, you can apply appropriate method in order to find out the initial exponential growth rate. And finally, if you incorporate Brazil and Russia, so Brazil is showing much more steeper growth rate, and these are some important component for estimating the parameter, or also having some estimate for initial exponential growth and other important issues. Now, if we look at the daily reported cases from one country to other country, and in forthcoming slides, I should stick within the same time range, that is from 15th of February to 22nd of July, then you can see different kinds of trend you can observe if you move from one country to other country. Trend means, in case of Germany, you can see that peak in terms of 7 days moving average that appeared near 31st of March. And peak is little bit sharp, and there is a decay, and then there is a little bit of oscillation. For the sake of brevity, you can try to estimate this part with a exponentially decaying curve, or with appropriate modeling technique, even you can capture this variability also. Now, if we move to from Germany to UK, then you can see that here, if we consider these as two local maxima, So in this case, you can say that in terms of 7 days moving average, the daily reported cases might have bimodal distribution. Of course, instead of 7 days moving average, if you consider some large number of days moving average, this peak might be removed. But how to cross verify, that means whether my model predictions or my model construction is correct or not, apart from these daily reported cases, at the same time you can match your solution trajectory with the cumulative number of reported cases in order to ensure that whether your approximation of this particular data trend with the outcome of a mathematical model is a good enough or not. And then you can see that here the first peak in case of UK that appeared at a later date compared to the peak that was achieved by the country Germany. And this kind of trend varies from one country to other country, that you can see in consecutive slides. Like, okay, in case of Italy, the peak appeared little bit earlier than 31st of March, and there is a sharp decay in the number of cases afterwards, and till today it maintaining some sort of low level. Why at this slide I'm talking about maintaining this low level? Because in next couple of slides you can see that all the countries not always showing this kind of decaying trend and maintaining at low values after the peak. And one example is Spain. Initially the peak appeared around 31st of March, then there was a decay, and now you can see there is a some sort of tendency to increase. And of course one can think about that second wave is coming, but as per my understanding, that is due to unlock operation, and maybe due to some sort of social behavior or social pattern, or some of them might not be taking some precautionary measure, or maybe some other reason there is a little bit increase. And this is not the right time to mention that, okay, this is the second peak for this particular country. Second wave is going to start. Next, if we go to the case of Iran, then you can see it shows a completely different trend compared to other, that means earlier country data what we have seen. So this is the data for Iran. And finally, if you look at the data for Brazil, as I have told earlier, that you can observe after every 7 days on an average, there is a decay and then there is an increasing nature. So one can think about this might be a dynamics of the form that periodic with increasing magnitude. But if you look at the 7 days moving average, it shows a different kind of trend here. Okay, now already Professor Sinha talked about simple epidemic models, but I just want to go through them once again quickly, just to give you some different kind of insights that will be helpful to understand the multiple scale models for epidemics. So I'm not going to discuss in detail. It is already, you are introduced to this one in today's lecture. So this is the SIR class, the classical Carmack-McKendrick model. And these are the important aspect already explained by Professor Sinha, that this factor, that is beta S0 by alpha, this actually determines the basic reproduction number. Now here I want to give you a little bit different kind of idea for the basic reproduction number here, that from where it is coming into the picture. It is coming into the picture from the fact that if you look at the differential equation for infected class, then the rate of change of infectives with respect to time might be positive or might be negative. It will be positive if beta st minus alpha is greater than 0, and it is negative if beta st minus alpha is less than 0. And actually at a particular time point when for this t your st is equal to alpha by beta, then you will reach at the peak of the daily reported cases. And apart from reproduction number is related with the initial stage. Another important aspect is involved with this kind of epidemic model, that is called effective reproduction number, and that you can calculate just replacing this S0 by ST, and then to observe that how it is going to change with the advancement of time, and that will give you the effective reproduction number. This is a simple numerical simulation with this choice of parameter values, S0, I0. Here R0 I have marked in red color only to give you a word of caution that this is not basic reproduction number, that is recovered class at t equal to 0. So initially we can assume that there is no recovered individual, and if you look at the progress of the disease, so the number of susceptible is decreasing and then approaching to an asymptotic value. Number of infected is started increasing and then reaches its maximum and then decreases, and in case of recovered, it is monotonically increasing and ultimately getting saturated to some particular value. Now the point is that this kind of structure or this kind of model is good enough if your total population size is very small, because then you can actually claim that all the parameters involved with the model is not changing from one region to other region. What I'm trying to say, maybe from one country to other country, maybe one state to another state, or maybe from one district to other district, due to there's some sort of homogeneous mixing or heterogeneous mixing, some sort of movement of the individuals, etc., etc. In case of epidemic modeling, another important factor you might be familiar with, that is called sensitivity. Sensitivity means that which parameter or what factors have most important or drastic effect on the system dynamics. In order to understand that, let us go step by step. We can change the initial values, we can change the parameter values and see how it affects on the disease propagation. And this is a simple plot of the effective reproduction number corresponding to the previous model. So initially for that model, the basic reproduction number, that is for flu in a boarding school in England. The appropriate description of the model can be found in the book by Carlos Castillo Chavez and Brouwer on Maya Marcheva's book. But this is an interesting fact that basic reproduction number is calculated is more than 3.5, and then it start decaying as an effective reproduction number, and the point where it is exactly equal to 1, the effective reproduction number, that corresponds to peak of the epidemic, and then there is a decay because your effective reproduction number is now less than 1. Again, instead of changing any parameter, if you just alter the little bit of the initial condition. So what is the constraint here? The total population size is same. That means 738 plus 25 is 763, and here also 758 plus 5 equal to 763. But what you can observe, that peak will appear at 2 different time points, and also a less number of initial infective results in little bit less number of height of the peak. Because if you have a close look, then you can see that this height of the peak is little bit small or little bit less than the peak that you observed for I0 equal to 25. Okay, now if we consider the change in parameter value, so change is very small. It is actually in the order of 0.0005. Then you can see there is a significant variation in the size of the epidemic, in the sense that peak, they are appearing at different points, and also time point, and also the height of the peaks are significantly different. And from here, if you calculate the cumulative number of infected, there also you can see some sort of variation, but up to the limiting sense, that means at a large time, they might be same but may not be same. But in this case, you can see that there is no death or other compartments is involved in the model. So therefore, in this case, I can tell you that size of the epidemic will be the same. That means total number of infected will be same in this case. But another interesting aspect is that sometimes due to some sort of behavioral change, there might be some change in the rate of disease propagation. And for that, the most significant factor is beta. That means how or at what rate infection is getting transferred from infected individuals to susceptible individuals. So that is some sort of simple way to mathematically model the lockdown phenomenon. So here I have plotted three different curves, one in blue color, another in black color, and another in red color. Initially, you can see only black curve because they coincides with each other. From this point and onwards, now you can see they bifurcate into three different branches. And this is only for the reason, in case of blue curve, what I have done, the value of beta remain constant. In case of black curve, what I have done, that all of a sudden I did not change the value of beta, rather from this point and onwards there is a decline in the beta value, and then it maintains a low value for beta. But in case of red curve, here if you have a close look, then you can see that at this point you have a point of non-differentiability, only for the reason that suddenly we can change the value from higher value to lower value. And in the next slide, you can see these are three different forms of beta that I have used in the previous simulation results. This blue curve for the simulation result plotted in blue, and black and red respectively. So in case of this black curve, you can see initially it was maintaining some constant value, then there is a small or slow decay in that particular value, and then it maintains a value like this. And if you look at the Wikipedia details for Germany, then you can find they have actually estimated the effective infection rate for Germany after collecting the data from different provinces and states of the Germany. And they have shown that initially there is a small growth in the beta value, then it appears attained at a peak, and then there is a decay, and afterwards it not settled down to a particular value, but it little bit fluctuating around some average value. So in this case, this black curve you can consider as a approximation of that kind of beta values. How we can ensure this is an approximation? If you calculate the area under this particular segmented lines and the curve they have represented, if those are same, so then you can say, okay, this approximation might be a good approximation, but you need to verify from the fitting of the model with the data you are having in your hand. Now, if we incorporate some additional compartment and with different kind of assumption, then you can see some different trends will coming up into the picture. So in the context of COVID, this exposed class is important. I'm not saying this is the final model. Rather, as of now, I don't know what is the total number of different models have proposed so far, but this is not the final model for my presentation. I'll come to a little bit complicated model afterwards. But exposed class is important. But once you incorporate an exposed class, what change you can see in the dynamics? Here, the understanding is that once infected are getting are coming in touch with susceptible individuals and infection is transferred to them, so immediately they might not develop the symptom. So therefore, they are latently infected, and that can be clubbed into a different compartment named as exposed. And what is the basic assumption here? That exposed compartment cannot spread the infection. So with this assumption, if you look at a sample simulation result, so this is the plots of 4 different compartments, and you can observe that black curve corresponds to exposed compartment, and what happens here, that total number of exposed individuals is higher than the total number of infected individuals. And the most natural question that might be coming in your mind, that if you assume that exposed individuals can also transmit the disease, what can happen? Answer is here. If you modify your model, that means susceptible to exposed compartment, that this propagation can have due to transmission of infection through to different channels. That means when susceptibles are coming in contact with I, and also individuals from E. But the point is that here we can assume if Q less than 1, then the intensity of infection spreaded through exposed class is less than the infection strength spreaded by the infected class. Then what you can see, that dynamics more or less seems to be unaltered. But if you have a closed loop, that means in the same plot, now if you plot the exposed class and infected compartment in the same graph, then you can see there is a significant variation. And if you look at these two slides carefully, so the parameter values are same, initial values are also same, only the Q value is introduced here. But with this, if you compare the exposed and infected compartment, then you can see there is a significant and clear-cut difference in the size of the exposed compartment, as well as size of the infected compartment, as well as the day on which the maximum peak will appear or maximum number of infected can be reported. And all of those things are influenced by the introduction of additional class here. And of course, in case of COVID, in the context of COVID, that if you want to develop a very simple model, still you need to incorporate one more compartment or one more assumption here, that there is some sort of disease-related death rate. For the crude assumption, you can assume that this is happening only through the infected class. And as the epidemic or endemic or pandemic, this is whatever you are talking about in the terms of COVID, it is a very short range data set that we have in our hand. So I am not in favor of incorporating demographic changes into the modeling approach, because those are taking place over a slower time scale compared to the faster time scale over which this COVID-19 disease is spreading. And now I can talk about a little bit about the COVID-19 model and what we have done so far. Just some sort of glimpses. So in this paper, we have considered a 5-compartment model, that is susceptible, exposed, infected. J stands for quarantined, and R is the recovered class. And what we have assumed, that exposed class and quarantined or hospitalized class compartment, they can also responsible for the transmission of the disease. And this 5-compartment model is actually tested for a data from a small region, that is Cali of Colombia. And then we have estimated different parameter values, and outcome is looks like this one. This blue curve is the simulated curve, and this dashed curve is the 95% confidence interval. And you just try to understand that a small variation in one of the parameter value that can affect a huge amount of number of predicted results. And this is only for the reason because once we did this analysis, that was at a very earlier stage. So data was taken only up to the middle of April. But if you do the same analysis as of now, then there will be a significant change in this particular curve that I am presenting here. But what is the main motivation behind this particular analysis? Another thing that you can consider, a little bit sophisticated model, there you can think about 3 quarantine class. So why this 3 quarantine class? Suppose some individuals from susceptible class, they traveled from one location to other location, and they are restricting themselves within home isolation or home quarantine without having any symptom or severe any indication. And after some time, they can come back to the susceptible class. From the exposed class, some of the individuals, those are tested to be positive. They asked to quarantine themselves, and some fraction might require some sort of transmission to hospitalization. And that's why this Q3 is not only the quarantine class, it is actually hospitalization class, and most of the contribution is coming from the infected class. And as a simplistic assumptions, what we have assumed, that death is related either from this Q3, that's mean hospitalized compartment only. And this is only for the reason because in our work, the group is concerned, 2 people who are actually medical person, and in their state, they ensured that as of now, the total number of hospitalization may be required. They can accommodate the hospital beds, and that's why we have assumed that death is only contributing from this hospitalized compartment, not from any other compartment. So that means medical intervention is good enough, and that's why no disease-related death rate from any other compartment apart from Q3. And what is the main outcome? If you compare the data or compare the outcome from these 2 results, so then you can see the total number of expected hospitalization by the end of April was predicted more than 13,000 if we consider 1 compartmental class, and on the other hand, it is only 3,500 if you consider 5 compartmental class. So the take-home message from here is that instead of waiting for severe symptom, if the individuals follow some sort of restricted movement and their health practices and they follow the guideline, then the pressure on the hospitalization might be less. That can be speculated or predicted, or rather can be proved, or some sort of forecasting from the modeling approach itself. Next, we must concentrate on the multi-scale model. That is why this multi-scale model is required. In this part, I should talk about the data from India only, but please excuse me that as of now, we did not work on data from India, but the same approach is applied to the data for Germany that I'll show you at the end. So what is the main motivation behind multiple scale? Let us look at the data first. So these are the different important aspects for the disease propagation, or also for the modeling approach, how to decide that which model will be most suitable. So then you should keep in mind that what is the total size of the population, whether there is any geographic variation or not, or there is some sort of variation in human behavior at different location. So depending upon that, you need to construct different patches or different sites or different regions for which you are going to write down your mathematical model. Why I am talking about these things? Only for the reason because India is a huge country, and at the initial stage, we cannot consider that the entire Indian population is susceptible. Rather, how the susceptible population can be calculated in a way that first case was reported in case of India was in Kerala. So the place where that person was arrived from China, and then he moved at the nearby locations. So population at that particular region can be considered as a initial susceptible class size. And once the disease is reported some other part, so population at those regions or those locality is required to be considered under the susceptible class and so on. And also from the data, you can see that there is a clear-cut different kind of trends that we can observe towards the growth of the disease propagation. So just as a simple tabular form, you can see that the dates on which the first reported cases was actually recorded in different countries. So in Kerala, it was reported on 30th of January, then in Delhi on 2nd of March, and so on. And latest, that is the latest case was reported for a state is at Nagaland, that was 25th of May. So that means what I'm trying to convey through this particular table, that consideration of population is Nagaland. If you want to model your state-wise, then consideration of population of Nagaland is within the susceptible class is not a good choice, because there was no infection up to 25th of May, but all other states, they have some reported cases. And on the other hand, these kind of states can be added step by step at different time points as when the initial cases was reported. And also, as Sita Proshina have mentioned, that all of a sudden that 14 individuals was actually reported in Haryana who actually came from different countries, and some of them they attended some social gathering. And that's why if you look at the initial number of reported cases, these are also significantly different. So not all the places it is exactly equal to 1. At some places it is 2, 3, 4 different figures can be observed as per reported cases. Now, if we look at the trend in Kerala, that is daily reported cases from 7th of March to 22nd of July. So then you can see initially there was an increase, then there is a little bit decaying trend, and after that it is always on a growing path. So in case of Kerala, if you look at the 7 days moving average, it shows a more or less continuous increase in the number of daily reported cases. But this trend, so here in case of Kerala, the total population is also different from some other states. And also the interesting point is that daily reported cases is not more than 1,200 as of 22nd of July. But if you look at the data for Maharashtra, so it already crossed daily 10,000 cases at some time point, and also it shows a continuously increasing trend. So what I'm trying to make a point here, the trend in Kerala and trend in Maharashtra is completely different. So if anybody wanted to model the epidemic spread in the context of India, the size of the population is large, and then estimation or assumption for the initial susceptible size, those are completely challenging issue. And sometimes there might be some sort of loophole which can propagate it over the time and leads to some sort of misleading forecasting. And again, if you look at the data from another state, say Delhi, you can see due to some sort of policy implementation, already in the state of Delhi, we can see there is a decaying trend only in the Delhi, but not any other states in India as of now. And these 3 pictures probably convince you that we need to think about at least the disease propagation state-wise instead of considering in terms of data from India. But actually, I should prefer, but data is not available as of now. You can think about maybe at district level, or the most important one will be hotspot level. But again, you need to go back to the approach that was introduced by Sita Proshina, that is network structure, and then generation of new hotspot is nothing but that is the random network, some new nodes and some new point of infection is appearing at different time points and at with different intensity. And now if you look at the data for last couple of days, that is from 1st of July to 22nd of July, from these 5 states, you can see they shows completely different kind of trends. And all of these individual trends of this particular states is quite different from the combined trend in India. And then if you incorporate few more, then you can see that these particular states, that is Maharashtra, Tamil Nadu, and Karnataka, as of now, they are showing much more higher trend compared to other states here. And if you incorporate all the states, so some of the states might be very close to the horizontal axis, but of course they have some sort of contribution. Now, how to have some more insight? More insight, or the or rather we can say that in support of the considering multi-scale model in terms of different time point and different size of the population, that can be clearly understood from these 2 consecutive slides. So here I have just plotted a pie chart for that state-wise daily reported cases only on 21st of July. So you can see that Maharashtra is contributing 21% of total daily reported cases across India. But now if you plot the number of deaths for all these states in the same order, then you can find that contribution towards the death from Maharashtra is much more larger compared to the percentage of daily reported cases. And of course, this is only a single day data. If you take this particular data for a long time and take an average, and from there you can actually estimate what is the average rate of death for different states. And then the idea is that, so first of all, you can think about, you have 1, 2, 3, 4, say 8 different patches. And for each of the patch, you start your model from different time point. Of course, their size of the populations should be different depending upon whether you are considering state or district or region, whatever may be. So initial dates will be different, and then if you can collect some data and also match your simulation result with the available data, and then you can club them in order to understand the trend at national level. So that would be much more accurate compared to the data that we can try to estimate from the data from India only. So how this can be done? Let us think about that these are a system of equations. Just for an example, we can consider the susceptible class, exposed class, infected class. This A stands for asymptomatic. So some of them, they might be asymptomatic. Q is quarantined or hospitalized, and R is the recovered class. And at the same time, I have written this beta J bar. Beta J bar is not only the force of infection, rather all the parameters involved with the J8 patch, and they should vary from one state to other state, or one district to other district, or one region to other region. And also the number of states those are active at different time points, that should vary with respect to this time point. So that means, for example, for Kerala, this T10 is some day in January. Then T20 for another state is, say, 2nd of March. Maybe on the 2nd of March, more than one state was activated in terms of number of daily or initial reported cases, and so on. So what we can do, that suppose for the model for patch 1 looks like this one. So here, just for the constraint of the place, I have just ignored the asymptomatic class here. But just think about, we can simulate this equation for the time interval T10 to T20. After T20, we can activate one more patch. So now J varies from 1 to 2, and these two models we need to simulate from T20 to T30. And if we proceed in this way, so after some times from T30 to T40, 3 patches we need to consider, and we can assume these parameter values are different, and that can be obtained from some appropriate reporting from different regions or states or districts, and some of them can be estimated from the data if the data set are reliable. And in this way, if we proceed, then ultimately we can take the sum of the different components from different regions or different patches, and then if we combine them as some sort of global scale or aggregated variable, that will give you much more better picture. And the idea is that from T10 to T20, these aggregated compartments consist with only S1K. This S1K corresponds to S1 at particular time point Tk. So therefore, in within the time interval T10 to T20, there is only one compartment that are contributing to the aggregated compartment. Then from T20 to T30, you can see that 2 compartments, that means compartment from 2 different regions, they are contributing towards the aggregated data. And finally, from T30 to T40, you will be 3 compartment or 3 patch or 3 state or 3 region. And if you proceed in this way, ultimately you can get the complete picture over a larger time scale. As the time points are different at which they are getting activated, their parameters are also different, and also the time of their activation is completely different at different location. So that's why it is called multi-scale model. But I cannot enforce you that this kind of model is always called multi-scale model, because some of the literature people talk about meta-population model also. That means at different location you have different kinds of dynamics. And now if you look at some sort of visualization that how it works like this, that suppose on the T10, one particular state is activated, and suppose your parameter estimation and everything is fine, you have correctly identified the initial exponential growth rate, you have correctly calculated the basic reproduction number, also you have correctly identified the size of the susceptible compartment at the initial stage. It shows this kind of growth pattern. Now at T20, another particular patch is now activated. It shows a different kind of dynamics compared to this one. Then at T30, another patch is now activated, and so on. And now if you collect just the data for number of infected day wise, so then you can see some sort of jerk or some sort of change in the trend of the exponential growth that will be clearly visible. So in this way, if we proceed, so at 4th point, another patch is activated, 5th point, another patch is activated, and 6th patch, another point is activated. But now for this one, if you keep on adding the daily reported cases on day basis, then you can see for the first window, that is T10 to T20, you can see this kind of growth pattern. Now on T20, if you incorporate the data from second patch, then there is a little bit of jump. And also you can see that this particular trend is completely different from this one. Then from T30 and onwards, if you activate one more, then you can probably have a close look, then you can see there is a little bit of variation. But of course, this curvature is little bit different compared to the curvature that you can see here. And in this way, if you proceed, it looks like the outcome of a SIR model, but actually this is an outcome of a multi-scale model itself. And also the point is that this is not fitted with any particular country's data, so that's why it seems to be smooth enough. But if you look at the realistic model, this is not smooth enough, rather it is a varying kind of thing. So this approach we have applied in the case of data for Germany, and then you can see the cumulative reported cases. This magenta color curve is the simulated result, and these blue bars, these are the actually raw data for Germany obtained from Wikipedia. And then you can see that from state level data, if we apply those kind of approach, that this fitting is quite well. And of course, we have compared with the number of deaths and other compartments also. So this gives a nice agreement with the simulation results or proposed model's effectiveness with in case of data from a particular country. So what we have done here, we have considered the different patch as a different states of Germany, and in the Wikipedia you can see that state-wise data is available, and also the effective force of infection is provided there. So all those details are used to estimate or obtain the parameter values for different parameters involved with the model, and then it has a very good fit with the data that we can see for the Germany. And finally, in case of India, what you want as of now, so there is some sort of movement from one state to other state by train or air or some other means, and therefore only disjoint patches will not work, rather connected patches, or say precisely the network is the most suitable one in terms of differential equation in order to simplify it. And then you can try to explore this as a challenging issue for the modeling. And then what will happen, that apart from this particular disease propagation at a particular location, rather you will have this kind of dispersion component, which actually takes care of the fact that what are the fraction of populations those are getting transferred from one location to other location. So you might be wondering that why in the first equation I, A, Q, R, these are appearing. These are appearing only for the reason because once a group of people moved from one state to other state, we don't know what is their demarcation into different compartments. But of course, if they are exposed or they are infected or they are somehow individuals who are qualified to be quarantined, so as per the model assumption, they can contribute a little bit towards the disease propagation. So this micromanagement is very much important in the context of different scaling, that is size of the population, time scale, etc. And that's why I love to call it as a multi-scale model for the disease propagation. And in case of India, as of 22nd of July, the total number of infected individuals is this one. Now, if you divide them into state-wise, you see there is a variation from one state to other state. And again, if you subdivide this state data from district-wise, just for Maharashtra, you can see there is a different size of cumulative number of reported cases in Mumbai, Thane, Pune, and Palghar. So some new spot may come up. So with these data, if you can manage from somewhere, that might be most effective model for COVID transmission in case of India. And as I have mentioned, that this is not the only modeling approach. With different kind of modeling approach. So instead of ordinary differential equation, you can think about some delay differential rate structure model or some other kind of model in order to construct this multi-scale model. And even hybrid model is also another important modeling approach. And individual-based model in a country like India is quite tough because it takes lots of simulation efficiency and some access to supercomputer in order to perform the analysis. Okay, with this much, I must stop here with some references. These are the 4 sites from where you get some data for COVID. These are 2 very good books I should suggest. If you are interested, you can go through them. This first book by Brouwer and Carlos Castillo-Chavez on just mathematical ingredients, and this book, that is Manfredi and Alberto Donofrio, these are important because social behavior or human behavior is very much important for the spread of infectious disease like COVID. And some other reference, if you want to have a more insight about the some complicated or other type of modeling approach that we have done so far, you can have a look at these papers. And just for having an essence of multi-scale model, you can look at these 2 papers. One that is global regulation of individual decision making, and this is the latest one, stochastic intracellular regulation can remove the oscillations in a model of tissue growth. These are not in the context of epidemiology, but whatever multi-scale idea, that is the concept, some preliminaries of multi-scale idea and few more references, you can have it from there. And this is the list of the names. There are few more with whom I have collaborated so far on epidemiology, but the name which are marked in bold, they actually dragged me towards the epidemiology business. But earlier I have started my career with ecology, but this person convinced me that, okay, we can try to do something on epidemiology. Thank you.
Thank you very much, sir, for giving such an interesting and insightful presentation on the transmission dynamics of COVID-19 pandemic. You very elaborately and extensively described how through multi-scale modeling mechanism, we possibly can address the problem of propagation of infectious diseases as time and location varies. The strategy, the model design in this way really can be very effective to combat today's pandemic situation. Thank you very much, sir, once again for your wonderful lecture. And
Thank you.
I see there are a number of questions already heaped up in the question and answer box.
So
Mr. Banerjee, can I ask a question, please?
yeah, sure.
First of all, my sincere gratitude to you for your gracious present and a presentation where the level of complexity gradually rose. So thank you. Now, with your permission, I'm going to ask a question which might seem a bit allegation. Please bear with me.
Yeah.
The numbers that were, the data that were reported were all absolute numbers.
Yes.
Now, for some, mystery, I come from a engineering background. For someone like me, normalizing by the total population seems to be a way to go. For example, India has 1 million now. Now, with a total population of 1 billion, the percentage is 0.1. Now, for US, they have 4 million. That's the total population with 400 million. It's 1%. It's an order of magnitude. Now, when I see the data, not just in your case, but most of the place, all the places, it is ranked in terms of absolute numbers. I'm just wondering what happens if it is normalized with the total population. Then, so if you could throw some light on that. For example,
Actually, I talked about this particular issue at the very beginning of my slide. If you look at the ranking in terms of total number of tests per 1 million or total number of tests over the size of the population of the country, there will be different kind of ranking. And another thing is that once we are talking about the number of testing, then what particular testing protocol you are using. So the testing protocol followed by US is different from the testing protocol followed by Spain. And that is a little bit different from the testing protocol used by Germany and so on. So of course, your question is a little bit related to the fact that whether these data are reliable or not. And of course, in case of percentage, you can scale the entire number of infected by the total population size. But in case of India, it is little bit tricky, because in order to have a significant number of change for the simulation, you need to choose very, very small time interval. And at that particular minute level, data might not be available. So with respect to the fraction, if you calculate your beta value, that means the force of infection will be rescaled. That means how you are going to define your model. That's why towards the end of my talk, I have mentioned that you need to choose your size of the susceptible appropriately. At the initial stage on the 1st of February, if you assume that the size of the susceptible population is equal to the size of the current Indian population, that is not an good assumption. As
That's understandable. That is understandable. However, let us say, I'm sorry to just continue just for a second. The Maharashtra data that you gave, just in the last few slides, different states.
Yeah.
And also in Maharashtra, the different, or the pie chart. Now, the pie chart is also given in terms of absolute numbers.
Yes.
So let us say if I redo the pie chart, normalizing it with the population of the state, is it
definitely that is going to change. That is going to change.
Now let me ask you why you chose to give the absolute number instead of the normalized number.
I have chosen absolute number only for the reason because in case of normalized number, if we consider, then there might be some sort of confusion, because within this time period, say 3rd of 7th of March to 22nd of July, there is a huge amount of death that is not related to COVID. Then that is required to be incorporated into this pie chart or not? That is another important question. So in order to be...
That amount of death is significant compared to the total population of the state?
It is significant, as well as it is also significant because COVID related death is only 1% of the total death reported there. So that means that might not be that much clearly visible if you scale over the entire state data.
Okay. Thank you very much. Thank you.
Okay. So let me quickly answer the question that I can see in the chat box. First question, anonymous attendee. Can we model epidemic with the help of linear algebra, the concept of eigenvector? I think, I don't know, but for some difference equation model, that is discrete equation kind of thing, that is in plus 1 equal to some constant into in, that might be one approach. But of course, this eigenvalue, linear algebra, eigenvector, those are coming into the picture in case of calculating the basic reproduction number and other stuff. Then Jonathan Bourbon, at this time, is it still correct to aim flattening the curve since we already have enormous number? Frankly speaking, that I have shown for a very simple model. Once there is a peak is achieved, but we don't know when we are going to achieve the peak, because new hotspot or new regions, they are coming up with some data, and as per the trend that we can see, you can expect flattening of the curve at some state, because already in Delhi you can see some sort of flattening, but immediate flattening as per Indian data is concerned, I think that cannot be achieved within coming 7 to 15 days. The next question is Ritesh Kumar Pathak. Please share the PPT. Oh, that is the organizer's duty. I'll send them the file. They can share with the participants. Then Devoshmita Mukherjee asking that, sir, regarding the herd immunity, I have read a recent news article that as vaccination is not available in the market now, so the only solution to control this pandemic. Okay, this herd immunity is a point to achieve. That is not a control strategy. Because as per my understanding, control strategy is something like identifying the infected individuals, giving them appropriate guideline, giving them the treatment, the people who need serious intervention at the hospitals or medical care, that to be given, and also confinement of the infected individuals such that they should not spread the disease anymore. So those control strategy is, as per my opinion, is much more effective, because herd immunity, whether it can be achieved or not, that is a controversial question. I cannot give you a clear-cut answer. And if the herd immunity is concerned, I can make a small remark that COVID is a one kind of flu. And if you look at other kind of flu, herd immunity is some sort of temporary solution, not a long-term solution. Even for influenza, for all the strain, vaccine that may keep you safe for more than 2 years, as of my knowledge, is not available so far. So I don't know whether herd immunity, how to achieve it, and once it is achieved, how long it will sustain. That is, of course, a questionable thing. Then the question from another anonymous attendee, does local administration play a role in determining the multi-scale model? Yes, of course, it can determine a role. As I have said, for example, local administration, maybe you can think about the healthcare services. If they are well equipped with PPE and other precautionary measures, so then you can think about at one particular patch, the disease propagation from the quarantine compartment is now get rid of. So in that way, and also if you consider the model that I have shown with 3 compartments, that people who traveled by train or flight, they bound to be confined within their room and not going to the market or roaming around. So in that sense, local administration play a crucial role in order to determining the some sort of effect, not determining the multi-scale model, rather it has an effect on the propagation of the disease spread. Then Shomit Ghosh is asking, sir, how these models will help us to prevent these things? Sorry, this model is just to capture the growing or decaying trend of the epidemic. Model cannot suggest any preventive measure. Preventive measure should come out from the medical practitioners or molecular biologists and even virologists and epidemiologists. Mathematical model cannot come up with a suggestion for preventive measure. The next question by Dr. Manav Bishas, when and how we shall overcome, this is a big question. This is might be some sort of award-winning question, I don't know. When and how we shall overcome the COVID-19 pandemic. Does your research give any? No. This is impossible. Rather, data from different countries already showed that they are able to control. For example, France, Germany, Italy, they are on a decaying trend. And as I have shown you that in case of Iran, it is a again Iran and Spain, they are on a little bit growing more, and universally acceptable solution still we need to wait. Then from Prashad, how to take into account of variable transmission rates. Okay, variable transmission rate, that you can get the details from the Wikipedia data for Germany, and they have cited two literature. I forgot the exact names, but they have actually explained how this variable transmission rate can be calculated, because they have the individual serological data set from where, and also contract tracing very well equipped with some sort of sophisticated software. So from there, they have calculated the time variable transmission rate. Then the question from Ritesh Kumar Pathak, sir, I have started studying mathematical modeling. How should I start to contribute in mathematical that one. Okay, send feedback. Probably I have answered all the questions that I can see from this particular chat box.
So no questions left so far, I think. So we have been listening to eminent speakers deliberating in the areas of mathematics for epidemiology since evening. All these valuable insights gave us a new perspective that we can adopt while discussing these issues. I hope it must have been a beneficial and enriching session for all of our participants. If you have any more questions in your mind, please drop in the discussion forum. We shall convey to our respective speakers. Now we are almost near the end of session. I shall request Dr. Taposh Ghosh to give vote of thanks and formally end today's webinar. Dr. Taposh Ghosh, please.
Sir, kindly unmute.
Can you hear me now?
Yes, yes.
Yeah. So thank you, madam. I deem it to be a, sorry?
Your voice is very low.
The voice is a bit slow, sir.
Can you hear me now? Is it okay
Yes,
now?
yes, it is.
Okay, okay then. So let me thank you again, Dr. Bishwas. And I deem it to be a great pleasure and privilege for me to express my sincere thanks and gratitude to all the distinguished panelists and participants who took their precious time to join the webinar today and participated actively throughout the sessions. And on behalf of the organizing committee and on my own humble behalf, I would like to extend heartiest thanks and gratitude to our Honorable Vice Chancellor, Sir, Professor Dr. Shoykot Moitro, for enlightening us through his inaugural speech and for always inspiring, encouraging, and motivating us in search of excellence. Thank you, sir. I would also like to thank Director of our school, Professor Dr. Shukhendu Shamazdar, for his thoughts and overview on today's webinar and for sharing valuable information in his lecture as appetizer in a dense form, sir. Thank you, sir, for your continuous guidance all through. And also special thanks to our eminent speaker, Professor Shitabro Sinha, for such an astonishing deliberation on an interesting topic like epidemics, networks, and games. And thank you for your elaborate explanation on mathematical modeling of epidemics, its dynamics, and citing the history of mosquito theorem from Dr. Ronald Ross. Also the models and strategies for vaccinations, the SIR model, and of course the theory of games. And what I can say on personal ground, I like the prisoner's dilemma the most. It was quite interesting for me as well, though I'm from the background of chemistry, so it was quite interesting. So thank you, sir, for taking your time from your busy schedule and sharing your work and ideas in today's webinar. Thank you, sir. I would also like to thank our other eminent speaker, Professor Molar Banerjee, for such an excellent informative speech on such a relevant topic. And thank you for sharing so many aspects and directions of mathematical multi-scale modeling of COVID-19 pandemic in such a lucid manner, especially the country-wise analysis of current pandemic situation. And you thoroughly discussed the numerical simulation for various models, SIR models, along with the other multi-scale models like ACIR models, ACIJR models, and the quarantine model. I truly believe that all our participants, be it students or researchers or faculties or practitioners of science and engineering across all disciplines, will take a lot of information and knowledge from today's webinar and the lectures definitively, and will explore them in their individual fields of expertise. I would like to thank both the speakers for taking the questions and answering them and discussing them elaborately. And I would also like to thank our head of the department and the coordinator of this webinar, Dr. Atrey Bishwas, for being there from the conception to the execution of this webinar, and definitively for organizing a webinar on such an interesting topic under current scenario. I would also like to thank Dr. Orijik Bagh for his active participation and moderation during this webinar through. And so all the panelists are graciously acknowledged. My sincere thanks to all the participants definitively for their patience and active involvement throughout the discussion and question answer session. And we are happy to acknowledge that today we have students, researchers, eminent faculties from different premier colleges, institute, universities across India, not only limited to West Bengal. To name a few, I must mention some of them because it means a lot to us, like SRMB College from Coimbatore, Central University of Kashmir, Mahatma Gandhi University, Central University, Bihar, Chandigarh University, Gurucharan College from Silchar, and also we have participants as researchers and faculties from Jaipur, Jodhpur, Tamil Nadu, and the list is quite long, believe me. And also from our own state of West Bengal, we have participants from Calcutta University, SN Bose Institution, Jadavpur University, and also MCKV Institute of Engineering and other affiliating colleges of MAKAUT West Bengal. And most importantly, I would also like to thank our technical support team, especially Prem Kumar, who is working relentlessly to organize so very many webinars for the whole MAKAUT group and making the job very easy for us with such an intensive technical support. And also I would like to thank Ms. Koel De for her technical support as well. And if I miss anyone in particular, I express my heartfelt gratitude to all of you associated with this execution of the webinar, and thank you all. Thank you.
May I make a comment at this point? It is really encouraging to notice after 3 hours from since the beginning of the webinar, there are about more than 280 participants still logged in for something related to mathematics. This is really an encouraging indicator. Thank you. Thank you, all the participants. It is really, really, it means a lot to us.
Thank you, sir.
Thank you. Thank you, sir.
Thank
Now,
you. Yes.
we are ready for the formal closure, I guess. And if Atredi want to have some remarks.
No, I don't have any remarks, so we can finally log off actually.
Okay. Thank you all.
The whatever feedback links and all those have been provided?
Yes, I think so.
Yeah, in the chat box, just the feedback links and the e-certificate link has already been provided, and the participants may form the feedback link and the feedback form, and then they will have the e-certificates. And I think it will take 2 hours or so, and they will have that one. So may I request Mr. Prem Kumar to put the feedback links on the screen, please?
Yes, sir. Thank you all, sir, for it.
Yeah.
Yes.
So thank you very much.
Yeah, thank you, sir.
Sir, is the link available, sir?
Yeah, it's available and I can see the link. Yeah.
Yes,
Yes,
sir.
it is visible on screen.
Yes.
So all participants are requested to take the note of the link or take the screenshot of the link and give the feedback. After that, the certificate will be able to will be able to download after 2 hours.
Yeah. So I have already told, and I hope they have listened to you and they will do accordingly.
Yes.
Yeah. Thank you all.
Thank you, sir. We will be waiting for 2 minutes so that all participants can write the links. And after
Sure.
that, we will close the session, sir.
Yeah.
Thank you, sir.
I think
Thank you,
I
Sukhendu,
think
sir.
we can leave right now. Yeah.
Yes, sir. Yes, sir. After 2 minutes, we will close the session.
Okay then. Thank you.
Thank you for the
Thank you.
wonderful session, sir.
Yeah. Thank
Thank you,
you.
Sukhendu,
Well.
sir. The certificates will be available to download after 2 hours. We are now just arranging all the certificates and the certificates are in the generation phase. Yes, those who have taken the note of the link, they can leave the webinar. Thank you. For more upcoming webinars, the participants can visit our university website, makoutwb.ac.in.
Prem.
Ji, hello.
Actually, some of the participants are asking certificate link is not working. So you can announce once again, like
What? All the
available.
certificates will be available to download after 2 hours. Yes, all the certificates will be available to download using the link after 2 hours. Kindly submit your feedback. Thank you all participants for attending the webinar. We are closing the session and all the certificates will be available to download after 2 hours from the link given. Thank you all. Mr. Saket Sarkarji, I am closing the session.
Yes, मैडम को पूछ लीजिए एक बार.
Yeah, almost I think 90 participants are there and they have I think noted down the
300,
links.
300 cross 300 sometimes.
Yeah. Okay. Thank you all participants for attending the webinar. All the certificates will be available in that link after 2 hours. Thank you all.